Hello everyone and welcome to another Zosin session. How about that? Let's do 18th day of Advent of Code in the Gods Temple. There we go. Snailfish. You descend into the ocean trench and encounter some snailfish. They say they saw a slakey. So I think I'm not gonna read it out loud because I noticed that when I read things out loud, it kind of messes up with my perception of what I'm reading. Comprehension rather, not perception, comprehension. So, maybe because so the speaking part of the brain actually interferes with the reading one. So I'm gonna just read it silently, and then after I comprehend it, I will explain the meaning of the problem. Not like anyone gonna watch that anyway, so whatever. Very interesting. So, all right. So we have some sort of a binary tree, and we have two operations that you can perform on that binary tree: explosion and splitting. I suppose they're going to be explained a little bit later. To explode the pair's left value is added to the first regular number to the left of exploding pair, if any. And the pair's right value is added to the first regular number to the right of the exploding pair, if any. Exploding pairs will always consist of two regular numbers. Okay, so let's actually give it a try. So this, we want to explode this thing because it's inside of four nested pairs. So here's the first one, second one, third one, fourth one. There we go. So here is the one that we need to explode. And this entire thing becomes that stuff. Right. All right. So first of all, so what I can see is that this entire thing got sort of merged together, I suppose. So exploding pairs will always consist of two regular numbers. Then the entire exploding pair is replaced with the regular number 0. Ooh, I see. So this is actually very cool. So this is what it becomes. Okay, so we kind of remove these things. Right, so this I suppose, is added to the left number, if any, and that one is added to the right number, if any, but we don't have the left one in here. So we're gonna, like, not add it. So then it's gonna replace with 0. Though the way I did it actually doesn't really explain it very well. Right, so first we wanna kind of replace it with 0, right? We are replacing it with 0. And then to the right we add 8. And to the left, we can't add anything. That's why we end up with this entire thing, which is exactly... Okay, so I think I understand what the fuck it is. So maybe I need to do like a couple of more exercises in here on how to explode the pairs, right? So here is another exercise. So let me try to do that myself. Okay. First of all, I replace this entire thing with 0. Right, 2 doesn't go anywhere, 3 goes into the left, and this becomes this thing, which is exactly what we have in here. Okay, so this is actually pretty good that they provide the examples, so I can just exercise my exploding skills, I suppose. Right, so this is becomes 0. Right, 2 doesn't go anywhere, 3 adds to the 7, and there we go, so this is what we have. Wait, they got me. Oh, this is actually pretty cool. So, to explode a pair, the pair's right value is added to the first regular pair and exploding any. So, okay, so it has to go like to the... Okay, that's very interesting. That is very interesting. All right. I'm sorry, my vibrator. So okay, so this one becomes like 3. All right, so there's also this one. So let's remove these things. 7, 3. I'm replacing this entire thing with 0, right? So this becomes 8. And this becomes 9, right? So this is how it explodes. I see, so essentially pair explodes, becomes 0, and its values, like shards, go to the, you know, go to the left and right direction. So, and if any pair is nested inside of 4 pairs, the leftmost pair explodes. So I suppose exploding pair is always going to be a pair of numbers, right? No matter what, it's going to be a pair of numbers. Hopefully. Right, so this one I did correctly. Cool. That's cool. So I think I understand the explosion part. So what is the splitting? Easy. So yeah, essentially you just divide the number by 2, right? If it's not visible by 2, the remainder 1 goes to the right. I see. That's cool. So, and essentially the idea is that you have to perform the addition of 2 trees, right? So these 2 binary trees, and addition is basically combining them into a new pair. But after addition, you have to perform the process of reduction, right? So you have to explode and split things if they're appropriate, right? So this is basically what you have to do. Okay, so here is the addition. So, and after addition, we find the thing like this, so it explodes. After explode, so I don't quite understand. Okay, so after addition, this thing explodes, this thing explodes, this thing splits, right? And this is the result of splitting. So any number greater than 10, I see. Once no reduce actions apply, the snail fish number that remains is the actual result of the addition operation. Okay, I see. Adding up a list of snail numbers, okay. Okay, so there's a bunch of examples. I see. So we have to present the magnitude of a number, right, to verify that it is the correct answer. And it's just like summing up all of the numbers within the tree, but also multiplying them by 2 every layer, I suppose, to also include information about the depth of the tree. I see. Okay, that makes sense. Okay. Very cool. So we'll need to parse first the trees and then do the operations and stuff. Okay. That's a lot of numbers. Very, very cool. Very, very nice. Okay, so let's go, I suppose. So we're going to be the sample. I suppose we can use this as a sample, right? New day 18. So also have to provide AoC 2021. So here comes the sample. I'm gonna copy paste this into, I think, a boom. And here is the input. Get the puzzle input. Cool. So, you know what? I kind of like, I really enjoyed the last time using just like Emacs for editing HolyC files. I think I'm gonna keep doing that. So, because I just cannot stand the TempleOS text editor anymore. I'm really, really sorry. Right, so I'm gonna just edit things in Emacs, right? And then when it's time to compile things, right? When it's time to compile things, I'm gonna go into TempleOS and just like try to compile everything. All right, so the first thing we wanna do, I suppose, is just read the whole thing, right? So we already read the whole file and we want to start splitting everything by line, right? While, oh my god, it feels so fast to just edit in the Emacs. Oh my god, this is so good. Okay, so greater than 1, right? Greater than 1, and then I can do SV chop by delimiter. SV, the delimiter is a new line, and we're chopping that into the line. And then I would like to test it, right? So I think we have something like print SV, and I just print the line. Wait a second. If you think about that, chat, that doesn't exist because I'm recording this offline. The HolyC is just basically C with some modifications. So I wonder if you can produce the source code that is both compilable by a C compiler and a HolyC compiler, so I can test this thing without TempleOS and then run it on TempleOS. That way I'm still continuing the challenge, but I don't have to use the horrible text editor of TempleOS and the horrible HolyC compiler without the type systems, right? Because in C compiler you have at least some sort of a type system. That is very, very interesting. So if I go ahead and just try to compile this entire thing with a C compiler, what's going to happen? So we have a syntax error. File format is not recognized, treating it as a linker script. All right, so that means I probably have to specify the language. Okay. So we don't have CD and directory and stuff like that, and all of that is only needed for TempleOS. So what I'm thinking, what if we introduce a macro, blasphemy, right? Right, and if it's defined, right, we're actually not defined, right? If it's not defined, we're going to include this entire stuff, right? U0, so let's actually do it like this. If it is defined, we're going to have things like type def void u0, right? Semicolon, of course. SV, okay, so SV is defined in a common HC, so I suppose, can I just in blasphemy include common HC, like so. Can I do that? Oh, right. Class. Okay. That is very, very interesting. This is a class. Oh, and default parameters. Look at that. Also default parameters. This is so sneaky. So can we use the C++ compiler then? So what if we interpret it as a C++? Okay. So also we have a lot of these weird characters that TempleOS puts into the code. I suppose it puts them precisely so the code is not going to compile with C and C++ compilers. I think Terry actually did it for these kind of reasons. Though I kind of know why these symbols appear. So if you accidentally press not space but shift space, it will insert that weird thingy that you just saw. This one, I think, and I quite often just notice that I press shift space. Right, so let me actually get rid of that. And this is the cursor. It's kind of weird that I know all of these symbols by heart already. So all of these weird symbols that TempleOS inserts, I just know them by heart because I've been using TempleOS for more than 2 weeks. This is the 18th day of me actually not using TempleOS, right? So I use it for 17 days. So yeah, it's kind of funny that I know all of that shit by heart. So, okay. We might as well actually do something like this. It's going to be int64t i64, and can I include something like std int all right, u8. Okay, what about u8? This is not how you do that. Oh my god. What the hell is wrong with you? Come on. So begin is a private within. Oh my god! Terry, you're a freaking genius. Wait a second. Oh my god. I was always wondering why the hell in TempleOS and HolyC there's no structs, and instead of a keyword struct, he's using class, but then it acts like a struct. It makes it difficult to take a HolyC code and compile it with the C++ compiler, because class by default makes everything private, and HolyC by default, if you use class, makes everything public. So if you just take HolyC code and use the C++ compiler, yeah, it will simply not compile because you try to access these fields, right? So in HolyC it's totally fine. All right. So, but I could switch back to C, but then I will miss the default arguments and stuff like that. So it's kind of meh. So what do I do? What do I do? Huh. I'm drinking coffee, by the way. So maybe we can actually cheat this system a little bit. I'm going to introduce public, right? And in here, if it's a blasphemy, I define public as public underscore. And if it's not a blasphemy, so I'd like to actually separate these two branches because it's not clear what goes where. Right. So, and in here, I just define public like so. So we're slowly kind of building up like compatibility layer for TempleOS, which is kind of interesting. I really like that. Okay, str2i64 was not declared in this scope. Oh, this is one of the TempleOS default functions. I think I know that. All right, let me quickly try to do that. So I'm gonna go in here and just define this thing like that. So i64, if I remember correctly, let me actually, oh shit, it's gonna actually remount everything. So I'm editing directly in the hard drive for TempleOS, so I can't just do that, unfortunately. So, all right, as far as I know, nah, let me take a look at the usage. Let me take a look at the usage. str2i64. So it probably accepts this thing, right? So it accepts the beginning, the string. Then it should accept the radix, right? And as far as I know, it has a default parameter or something like that. But yeah. And then we have something like this, right? So endpoint, if I remember correctly. And we can reuse something from the standard library, can we? Can we reuse something from the standard library? So basically str to imax, str to imax, and right, because it's 64 bits. It is 64 bits. So then we have, it's even the order is actually slightly different. So Terry basically considered everything. All right, I'm not sure if it's gonna work though. We're gonna give it a try. All right, so str2 was not it's still not declared in the scope. I'm surprised. Did I do something incorrect? Because I should have defined it before I included common.hc. Okay, so that's fine. What else do we have in here? So this thing is probably defined in here, right? So we have to include this entire thing. Okay. And here we have an interesting situation, right? So we have invalid conversion. TempleOS uses U8 star, but here we're trying to do const char. I wonder if I can just like straight up do this, right? Even though it's C++, I'm using C conversion anyway. Endpoint, let's convert it like that. Hopefully it's not going to introduce too weird of the undefined behavior. Boolean. Okay, Boolean should be easy. All right, so we do type def Boolean as big Boolean. And as far as I know, there's a couple of additional constants, like true is true and false is false, right? So that's the usual thing in TempleOS. Okay, so there's some problems in here with that stuff. And I don't really know how to solve that, honestly. Because in TempleOS it is totally fine to do things like that, but you can't. And if I try to just cast this thing, right, if I just cast this entire thing, I don't think it's gonna work really well, right? It is something that I have to just deal with. So it's a flag permissive. What if I just enable that flag? Permissive, there we go. So it turned it into a warning. Okay, so let's actually keep it as a warning. Okay, memcmp, let's implement that. So yeah, maybe eventually I'm gonna rewrite the whole TempleOS in C++. So memcmp, I suppose it takes i64, right? And then it probably accepts U8, so pointer 1, and U8 pointer 2, and then the size, i64 size. Right, so let me take a look at the memcmp function. So it's located somewhere here, and then I'm gonna return this thing. Okay, ptr, and here is the size. There we go. So let me see. Okay, so there's another one. So memcmp, if I remember correctly, it's located in string stdstr. There is no such thing as stdstr, there is string. Okay, so this is a warning. File read. Okay, file read is very interesting. How can we implement that? I think I'm gonna just implement the classical like fseek to the end, ftell, malloc the entire thing, and fread. Right, so because file read is essentially just slurp the entire thing into the slurp the entire thing into the memory, right? So we can easily implement that, hopefully. Though it's already not complaining about common, which is kind of cool. I really like that. It's not complaining about common. So let's go ahead and implement this thing. So this thing should return that. Also, it accepts the file name like so. And also it accepts i64 size of the file. Also, if I remember correctly, it accepts the attributes or something. I'm not sure if the attributes is i64, but they're usually initialized with null like that, so we usually don't use that. So yeah, so I think for the compatibility layer, it's not really that important to have it. So there's one problem with default parameters of HolyC, and that is HolyC allows you to have default parameters in any place. I can have things like that. Right. C++, I think it won't allow you to do this kind of stuff, but HolyC allows you. And the way you can actually call this function, you would call it like this, right? So you will essentially call it like this. So you determine the position of the argument by a comma, right? And I think this is not going to work in C++, unfortunately. So we have to try to use default arguments like we use them in C++ if we want to use the the host operating system for development. Okay, so let me try to open a file. Right, so it's going to be fopen and a file name, and I provide the reading as bytes. Might as well actually assert that f is greater than, actually not equal to null, right? So it's more correct, like this. So then I'm going to do assert, right? Assert. So, and what are we doing here? The next thing I need to do, I need to fseek, right? So let me take a look at fseek. Fseek. Oh, right. So offset is going to be 0, and then we're going to have seek end, right? So let me actually do something like this. Return has to be equal to 0, I think. I think that's the assertion that we have in here. Then we have to do ftell to get the position of the cursor, and the position of the cursor effectively going to be the size of the file, right? Because we are at the end of this entire thing, right? Okay, but it can also fail, so we have to assert. We have to assert that m is greater or equal to 0. Right, and after that we need to allocate enough memory. So let's actually do something like this. So this is going to be buffer, and I do malloc, and I malloc this specific amount of stuff. Then after that we want to assert that buffer is not equal to null, otherwise we couldn't allocate this thing. Okay, cool. So now we have to bring the cursor back to here. So seek set, if I remember correctly. Then I'm going to assert that this thing is still 0. Right, and then I have to do a read. Read 8 like this. Okay, so something. Yeah, my auto formatter decided to actually format it properly. So this is the buffer, right? So this is the size of the buffer, and this is how many buffers we want to read. We want to read a single buffer, and then we return f. As far as I know, read returns how much it read, but it doesn't indicate the error. So the error is indicated by doing f error, right? Because C is dumb. It's a very dumb language. After that, we're going to close the file. Closing file can also fail for a variety of reasons, probably because the I/O in C is buffered, right? So when you close the file, it basically needs to flush everything, and if it couldn't flush, the closing the file will also fail. But I think at that point, I don't really care, so I'm just not going to check for failures in fclose, I think. Though I can try to do that. I mean, I have a return variable that I can just like do something like that. It's fine, I suppose. It is fine. So, and then I can just return the buffer, but it's quite important to return the size as well. But it makes sense to return that if the user provided the size. So if the size was provided, we're going to assign it to m. So here is the simple function that just reads the whole file, just slurps the whole file into a malloced memory. And it's your responsibility to free that memory afterwards, right? So hopefully I didn't make any mistakes. I mean, the compiler will tell me, the proper compiler, by the way, with the proper type checking. And we're using C++ compiler, by the way, which has a stronger type system than C, right? It's, very picky about the types, much more picky than C. And that's what I like about C++ compiler, right? Okay. There's a lot of reasons I don't like C++, but I really like the stronger type system, that's for sure. Okay, so maybe we want to convert this thing like that. Since it's a compatibility layer, we can do all of these things, right? I think we can. So conversion, so this is just turned into a warning. an initialize an argument of const char malloc was not declared. Okay, so let me do the following thing. So it keeps complaining about things, so it doesn't matter. Alrighty, so it's just a conversion. Oh yeah, this one has to be something like this, of course. That is very easy to fix, but I'm not sure about that one. Oh yeah, I'm an idiot. I have to do const char instead. Sure. Can I just do something like align assert? I can. Thank you, Emacs. Very cool. I wouldn't be able to do that in TempleOS, that's for sure. So here's this is just a warning, whatever. Don't care. Oh, there we go. We're already having benefits of using proper compiler. HolyC wouldn't complain about that, by the way, right? Because it doesn't check the types. But this thing checked the type and told us, bro, you're passing it by a value, but we expect the pointer. What the fuck are you doing? Right, so let me see. So we also have free. To be fair, free is basically just like a regular C free, so I might as well just do something like this. Should be easy peasy, lemon squeezy. Oh, and this one. Okay, so this one is very interesting. So TempleOS allows you to just call a code outside of main. And also it allows you to call functions without parentheses. So this is something that we'll have to take into account, unfortunately. All right, so, but we have a blasphemy thingy. All right, so if I do if blasphemy, I can quite easily just define a main, right? So nothing can stop me from defining a main. And in here, I'm going to just call it part 1, right? And maybe also part 2. There we go. So otherwise, well, I mean, I probably want to just do that. Otherwise, we're going to do it like that. Okay, so since we're compiling in the blasphemy mode, everything seems to be compiling. So can I also run the entire thing? So it got me the a.out. So I think I want to actually call it slightly differently. I think I'm going to be calling it main. There you go. So here is the main. And what if I run main? Okay, so assertion failed. We read this thing with an error. Oh, okay, so the assertion has to be no error. Okay, so we assume that there is no error in here. Cool. And nothing happened in here. I wonder why. I really, really wonder why. Oh, I think I know. In TempleOS, so let me take a look. It doesn't even complain about that. What if I try to do that with Clank? Clank should actually catch more errors. Oh! And GCC didn't even tell me about that. Yeah, so TempleOS, I mean, HolyC allows you to do this kind of stuff. Yeah, so we have to be super careful about that. So what if I do GCC but W all? Right, can I do that? Yeah, okay, so we probably want to enable as many warnings as possible to actually develop such thing. Okay, so it should be really easy to, you know, that. Simply, okay, so simply don't use this feature of TempleOS. It's not even that important of a feature, I think, in my opinion, in my humble opinion. I know that people like this kind of stuff, but I really don't care, right? So I don't think it makes that much of a difference in terms of the programmer performance and readability of the code. Because again, in terms of the readability of the code, right, so it is super easy to just format your code to look like this, which is very close to that, right? I think that feature doesn't really give you that much in terms of readability. You just like organize your code like that and it's almost the same, just with extra characters, right? I don't know. It's just me. It's my opinion, my humble opinion. Okay, so we have this stuff and... okay, so this is what I was worried about. Yeah, so there is a syntax sugar in TempleOS that allows you to do this kind of stuff. But as far as I know, it's nothing more than a syntax sugar, because this syntax redirects to just print, which in reality, I think it acts like printf. So you can quite easily just do something like define print, printf, You can probably even do it like that, right? Literally print into printf, and it's literally printf. Right, let me see. Okay, it works. It's pretty cool. But I mean, does it work in TempleOS? That's the good question. So an expansion of macro. So to conversion from, it still doesn't like that. It still really doesn't like that. Oh, I see why. Okay, so what about clank? Can I just do clank? So clank is a little bit more clangy about this kind of stuff. It just simply does not allow you to do these things. To be fair, is space is kind of complicated, because what it does essentially is x equal to space or x equal to new line. Right. I mean, yeah. File read. No matching function. Okay, this one is very interesting. Oh, all right. Clang is a little bit more strong in terms of like these things. Right, because in C++ you have a function overloading that dispatches functions based on the type of their arguments, right? So if you take a look at our compatibility layer, right, so this thing accepts U8, U8 pointer, but you calling it with the const char, which is rather interesting. So because of that, it cannot dispatch it properly. It just says that there is no such function. I have an interesting idea. What if I define overloaded function like this? It's a compatibility layer, so who cares? Const char, which basically just redirects into this one. Right. Into this one. Oh, where we basically, where we cast const char back, where we cast this thing back to const char. So it probably would make sense then to actually define this thing like that, and then have an overload for this thing, right, for this thing, where we cast it to here to achieve the proper dispatching. Okay, I think that's the thing we can do. And I think now it will... Okay, so we managed to actually make this entire thing compile without any warnings, which I'm super happy with. It's kind of cool. But we don't have a new line. So let me see. Can I do something like print new line, right? And there we go. So now we have that. So I kind of want to save this as a building script. So let me do it like this. Build sh. Right. So this is going to be bin s. What are we waiting for? Emacs. What the hell? Set xe. All right. And maybe I actually don't want to do it like that. Okay. So can I just do build sh? The cool thing, like I'm editing everything in FAT32 file system, right in the hard drive of the TempleOS. The cool thing about FAT32, when you mount it to Linux, it's always like executable. I think you can instruct it to be always executable, right? So how do we do the mount script? Wait, I said that it's read-write, but it also said the executable, I guess. I don't know. But yeah, I don't have to set the build script to be executable. It's executable by default. Thank you. Very safe file system. Cool. But the question is, does it still work in TempleOS? Right, so we came up with some sort of a compatibility layer, right? We came up with some sort of compatibility layer, but does it even work on TempleOS after all of this? Let's give it a try. So, yeah. 2021. Okay. So, now if I open this entire thing and main.hc, can I run it? It works. So I came up with a code that can be compiled by both C++ compiler and HolyC compiler. That is absolutely beautiful. I really like that. So there's something weird in here. I don't know why, but okay. So maybe some tabs were inserted in there or something, but maybe we need to like realign everything. But that is very, very cool. So yeah, now I can just have a proper compiler, right? And still run all of that on TempleOS, right? So we have a compatibility layer. But the question is, can we extract that compatibility layer to like a separate file or something, right? So because it kind of pollutes the source code. Alrighty, so let me go into MNT, home, AoC, in HolyC, and let me try. So this is going to be blasphemy, so I don't know, CPP, because it's a C++, right? And well, in C++ you have implementations in header files as well quite often because of the template bullshit, so we might as well just do this. If not defined, blasphemy, how do you spell that? Blasphemy HPP, you define that and then end if, right? It's just like include guard. So I'm gonna go to main.hc, and here is my blasphemy layer. Right, blasphemy layer. So, and might as well, did I include it? Yeah, okay, so I have an idea. What if I include it along the rest of the stuff? Right, so we have a basically blasphemy and common and template and stuff like that. Maybe I'm gonna call it HPP. No. Okay, so because FAT32, like it has problems with like, I think, capitalization with the casing. Compatibility layer, C++, HolyC, compatibility layer for C++. Yeah, for C++, essentially. All right, so that is very, very interesting, though. Okay. My brain is moving very, very fast right now. So we can just do blasphemy HPP, and there we go. So it's quite important to define this public thingy. All right. So, and maybe it makes sense to move this script into the common things as well. So I'm not quite sure. So how should I call that? So there's a blasphemy.hpp and then also blasphemy.build.sh. Blasphemy.sh. So should be fine, right? Blasphemy.sh, right? And it allows me just to build this entire thing. Okay, and it seems to be working, right? It seems to be working, and then I can just run it. Okay, cool. Then if I run AoC, so let us see. And if I try to run this entire thing, it's still working. Okay, that's beautiful. So we have a code that is cross-compiler, truly cross-compiler code. That's very cool. All right, so I spent like 40 minutes on doing that. So let's make a small break and actually get to solving the problem finally after the small break, right? All right, so let's go ahead and try to solve the problem finally. This time I'm going to be using a proper text editor with a proper compiler, right? But I'm still doing that for TempleOS, of course. Yes, of course. It is still TempleOS. It's TempleOS. It's a TempleOS challenge. It is. Okay, so what I'm thinking is that we can organize some sort of like a binary tree, all right? So, but for the binary tree, we'll have to define the class. Oh, goddamn. And I'll have to use that like public thingy now from now on. God damn it. So let's define a node, right? So here is the node, and for the node, I'm going to define public, right? So here is the public, so we're going to store the number there, right? Some sort of a value. And we're going to have a left and right subtrees, right? So left and right subtrees, if that makes any sense. Though you can have either a number or another node, right? So this is kind of a situation that you may have. So because of that, we may have a slightly... So I suppose a number simply doesn't have any left and right. So this is how we can represent that. Right, so I was thinking, do we need to distinguish between just like a pair and a value? We don't really have to, right? So if left and right both, you know, both null, that means it's going to be a value. But what's interesting is that if you have this situation, right? If you have a pair always has left and right, right? Pair always has a left and right, which leads me to believe to a very interesting thing. Right, could we actually interpret that? Not really. So I was thinking that maybe if we store these things as, you know, as a union, right, so we could interpret the value in here as a value, or maybe as 232b indices within the pool of the nodes, and that could act like a pointer or some sort, right? So, but we'll see, we'll see. For now, I'm gonna just do it like that. Maybe this is not an optimal representation of the tree, but I'm gonna go with it for now. Right, so also let's define the nodes capacity, right? Because I'm going to be allocating the array, not array, but rather the pool of nodes, right? So, and let's allocate like 1 kilobyte of nodes, and let's define them in here. So here's the nodes capacity. So, and it would be also nice to have something like nodes size, right? And we probably want to be able to allocate those nodes, right? So something like node alloc, right? And essentially what this thing is going to do is going to give you the next node, right? So something like nodes as size plus and return the pointer to the thing. It feels so good to use proper text editor. Oh my god. Oh, finally. So nice. And what I want to be able to do, I want to be able to also print the tree somehow, if that makes any sense. So let's actually implement that thing. Print node. Here is the node. Right, and in here, and in here, the thing that worries me is that if you have left, you always have right. That's what actually worries me a little bit. If you have left, you always have right. Which kind of creates like a very interesting situation. Can we just merge these two things together? Can we just do that? I'm not sure. Right, it would be kind of nice if we could. It would be kind of nice if we could. All right, because like how can I distinguish that node is a number, right? So I need to check node left, and if it's available, I know that node right is also available, so I have to do some weird stuff, which is really strange, but okay. So we can do things like that. Print the node value, so here is the value, and then here we can do something like this, right? So this is going to be more of like a print, right? So this is a print, then print node, right? Here's the node, print this thing, the left one, of course, then the right one, and then the closing thing in here, right? The closing thing. Okay, so that's the thing we have. Can I build the entire thing now? Blasphemy sh. Okay, oh, this one is interesting because it has to be something like LD. But the question is it going to work in TempleOS? I'm not really sure, but we'll see. We'll see. Oh, also another interesting thing is that this thing is not necessarily zero initialized, right? So we want to be kind of careful with this stuff, right? So this is the result. Maybe one of the things we want to be able to do is like zero initialize the entire thing. Mem set result 0 size of node, right? So we do that, and we don't have a mem set, right? Okay, that's fine. We can add that to the compatibility layer. So I think it's u0 mem set. We accept the pointer, then we accept i64. Like, I don't remember what it is, to be fair. God damn. Okay, so let me start the temp.os. Mem set. Let me jump there, and mem set. Ah, it's so bad. Destination, okay, value, and both of them are i64. That makes sense. Okay, mnc home AoC main.hc, there we go. And what I was doing? Oh, memset, right. So this is the value and this is the size, right? So, and in here, what we have to do, we just have to do memset pointer value size, right? Nothing special. But I didn't check if the memset returns anything. I think in C, memset can return something. Yeah, it does return the pointer that you provided in here. So probably for some sort of convenience. And I wonder if temp.os does the same thing. I missed that one. I didn't even look at it because the font is terrible. I just don't want to even look at that font. Please get it away from me. I looked at it for way too long. Okay, it does return this thing. I see. All right, so let me try to run Emacs. And if I go to mount AoC. All right. mnc home AoC 18 main.hc. Right, so here is the main.hc. And okay, so blasphemy.hpp. We have to return this thing. Cool. And now I can do blasphemy sh. Right, so what do we have in here? Memset cannot initialize blah 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 blah. Okay, sure. Let's cast this entire shit. What do you want from me? No matching function result. Oh, are you serious? Man. Okay, so this is what you have to do, in fact. But since it's a compatibility layer, who cares, right? Nobody really cares, I think. Because you can easily cast to... Yeah, so that's what you have to do. All right. Okay, that's fine. And we set everything to 0, and that allows us to do things, right? Which is cool. So before I go and do this thing, I want to kind of allocate a bunch of nodes, right? So if I allocate node alloc, right? So this is going to be just node x, right? I'm just allocating a node. And then I'm going to try to print the node. What's going to happen? I just want to see what's going to happen. There we go. So we have a used variable, but it just printed 0. But one of the things we want to do is assign a value as 69 and print it 69. Okay, cool. So we might as well do something like left node alloc, right? And within that node alloc, we also want to set something, right? So left is going to be value 69, and this one is going to be 420, right? And if you try to print this entire thing, it printed new line for whatever freaking reason, because I put it in here. So the question is, will that shit work in temp.os? I'm really curious. But yeah, as you can see, we can now recover this entire thing. AoC in HolyC. Okay. I'm really sorry. Okay, so we have that, and it didn't work. Okay, so there's some problems. Print. Oh, okay. Sure. I'm sorry. Oh shit, I'm sorry. And now it works, as you can see. It's just that. But it actually said 0 for whatever freaking reason, and I wonder why. So that's kind of weird. I incremented size, but left. Okay, so this is because of right. Did I not notice that? Am I that dumb? I think I am that dumb. Right, I literally just skipped that. Okay, so now it says 69 for 20. Cool. Into home. There we go. Okay. Thank you, Tempo. That's very cool. That's cool. I really like that. It's kind of funny. Okay, so we can now print these things and whatnot. So if we want to try to parse something, right? If we want to try to parse something, how are we going to be parsing it? Probably recursively, right? So let's do something like this. Parse tree, and we're going to accept the pointer to the SV, right? So here's that. Right, and essentially here we chop the line, then we're gonna have a node, parse tree, we provide the line, and then we want to print node. Did I say print node? Or I should have actually called it print tree. I like it better. And it's super easy to refactor things. I love it. My god. I can just move around and refactor things, and just like, there's nothing that can stop me. TempleOS is not going to stop me. All right, so unused parameter, which is fine. Thank you so much. All right. So I suppose the way we're gonna do that, right? So if SV, if SV, it's always going to start with something equal to this, right? We're going to parse it as a tree, right? So we'll have to do something like SV chop left, rather, right? If I remember correctly, in the common, we have something like chop left. Yeah, there we go. So I can chop one character left and remove that. After that, I can parse a tree. So it probably makes sense to allocate a node, right? So this is going to be a node, right? And it makes sense to always allocate it, right? So yeah, we're going to always allocate it. Alloc node. So all right, then I do node left, parse the tree, right? So we're going to have that. We parse the tree. Then I'm going to chop yet another character, which is the comma, right? Then I'm going to chop the right subtree, and then I'm going to chop the last character. So essentially, I'm chopping this thing, skip that, skip that, skip that, right? So that's what we're doing in here. Cool. Because they're compact, right? So there's no spaces between them or anything like that. We can just skip them. Okay, so, and the next thing we need to do is essentially chop the i64, right? The way we can do that is essentially node value sv chop i64, and I can just provide sv, and I think it will just work correctly, and then we just return this entire thing. So we just managed to parse the whole tree. So let's try to make it compile. Node alloc. Okay, a sv chop left. No matching function is sv chop left. Are you freaking sure, buddy? In the common module, common sv chop left. Here it is. Here is the thing. So probably maybe no matching function candidates. Oh. Yes, TempleOS would not tell me. TempleOS would not tell me. Thank you so much. This is so fucking cool. Oh my god, it feels so great. Finally. No matching function parse tree. So let me see again for the same reason. Right. but it's a bit annoying that in C++ you can overload functions, right? So print tree, you have to actually print the node, and you don't have to take the pointer. Cool. Oh my god, it just caught all of the errors, all of the mistakes I made, and I just like miss it so much. All right, so it printed pretty much the same shit, right? So, but since we parsed everything ourselves, so we can quite easily replace those things with that, right? And that kind of proves that we parsed everything ourselves. Right, we can also replace it with, I don't know, these things. With these things, and we can also print how many nodes we leaked at the end. Print leaked LD nodes, LD nodes, and nodes size. There we go. So probably want to put like a new line in there, of course. So that's how many nodes we leak. 180 nodes. How about that? That's a lot of nodes. So I want to see how this works in TempleOS. Okay, so let me see. It might not compile properly at first, but we can always adapt. It worked first try. Look at that. That's actually very cool. So I do have a compatibility layer now, right? So I can write HolyC code outside of TempleOS and then easily, like, quickly port it to TempleOS, right? So, yep. Yep, that's very, very cool. Who needs like a separate HolyC compiler when you can just use C++ compiler? Come on. Nice. Nice. Oh, yeah. Okay, so we probably have to remount everything. Can I just remount it? AoC, and if I try to save that, probably I want to revert the changes, just in case, because it was modified. Okay, so that's cool. Very, very cool. So what we need to do, we parsed everything, right? So we have this entire thing in our memory. And we just need to be able to add those two things together, I suppose, right? So adding two nodes, right? Add trees, right? Add trees. It accepts the left one and right one. And adding two trees together is essentially just allocating the node, right? You're just allocating the node and allocating the node, and then just assign left to the left and right to the right, and you just return the entire thing. That's literally adding two things together, isn't it? I think that's it. So, and in here we can effectively do this thing, right? So I can take first, so node 1 and node 2. Node 1, node 2. Right? So I just want to check if everything works as I expect it to work. Node 1, node 2, add trees, node 1, node 2. Right, so if I just run this entire thing, so here is the final result. So we added them together. Cool. So, and I suppose one of the things we want to be able to do, we want to be able to reduce trees, right? Reduce the tree, right? So we have something like this. And the question is, how would you even do that? So the whole algorithm is essentially just read the first tree and you keep reducing it, right? You keep reducing it. And the last thing, you need to compute the magnitude of the final sum. All right, so it's going to be I64 magnitude node root. And we're going to return something like 69 for now. Right. So the whole algorithm in here, if we understood everything correctly, right? If we understood everything correctly. Let me see. So this is the sum, right? So this is the sum, and it's initially null, All right, and then we can have an argument, which does not really necessarily have to be null, but we'll see. Right, so we parse in the tree, and here is the argument. If sum is equal to null, we simply assign the argument to the sum. Otherwise, we're doing the following thing. Add trees sum argument, and then reduce tree, and assign it back to the sum, right? And then for the part 1, print part 1, it has to be LD, we do magnitude of this sum. So yeah, so I literally just coded whatever it is set in the description, right? So, and I suppose we need to just implement all these things. I'm not sure how slow this entire thing is going to be, right? But we'll see. And I'm not sure if I'll do that stuff correctly. So here's the root, which is unused variable. Parse tree, so we have to provide unused parameter root. Well, I mean, no viable parse tree. Oh yeah, this is because it has to be like a pointer in here. Okay, so there's a warning, unused parameter, that is fine. All right, and let me see what's gonna happen. Though I'm thinking maybe I can actually compute the magnitude right away, because it sounds like a very easy thing to compute. The only thing I'm worried about is the wastage of the nodes while doing all of that, right? But maybe we can just allocate shit ton of nodes, right? I don't know, like 32,000 nodes, right? Who said we cannot do that? If we're gonna have some problems with wastage of nodes, right, and we're gonna run out of memory, I can implement a simple deallocation, right? So we are allocating objects of the same size, and the allocator for the objects of the same size is actually super easy, right? So I implemented that before, I can probably do that. So every time we need to deallocate the node, I can quite easily just deallocate it and add it to the pool of free nodes, and so on and so forth. It should be pretty straightforward. Right, so simple allocation of our nation. Okay, reduce the tree. So if any pair is nested inside 4 pairs, the leftmost such pair explodes. All right, so leftmost. If any regular number is 10 or greater, then okay, so we're essentially just checking for that. So the leftmost means that we're just doing the recursion, right? We're just doing the recursion and just exploding this entire thing. Though then figuring out how to add this thing to the left is gonna be very, very painful. Splitting is easy, right? Splitting is super easy. But exploding, okay, exploding is very interesting because you actually have, oh my god, that's, All right, so I think this is where it gets very, very interesting. Reduce a tree, right? You reduce a tree. And do you always return a new tree or something else? So let me, for splitting, split if any, the leftmost such regular. Okay, so let's actually go ahead and implement something like splitting. Note split tree. Split node root. There we go. If so we also need some sort of an indication that splitting has happened, right? So we need an indication that splitting has happened and a new potential tree that that might be modified. So the explosion doesn't actually let me go. That doesn't let my brain to go, because explosion seems to be like a very interesting trick. Right, so let me see. If I have something something like this, right? So this is going to be the structure, right? And I have to do something like this, right? So there's no right in this one, right? So there's no right in this one. And I know that I need to explode this thing. Right, I need to explode this thing. So that means I need to go up in here and go back in here, which is kind of painful, right? What's interesting is that the tree is organized so all of the numbers, 1, 2, like 3, 2, are leaves. Only leaves are the numbers, right? Only leaves are the numbers. And this thing is just like defines the structure. Right, so can we just store this entire thing in some sort of an array, right? 1, 3, 2, and then just have some sort of like information on where this entire thing is located or whatnot. But probably not that easy. Probably not that easy, because if you split something, it will affect this array and you'll have to like extend it somewhere here, right? So it's not particularly convenient to do it like this. It's not particularly convenient to do it like this. So we need to have an operation that can just like go one leaf to the right, right? How can we have such operation? That's a very good question. Okay, so essentially, if you are in here, you can go up and you can try to find that thing in the right until you have to the right. I see. So during the explosion, right? During the explosion, we are in a recursion. Okay, so I think I can pull that off. Right, I can pull that off. So when we do explosion, we just do in DFS, like leftmost DFS, until we found the thing that we want to explode. Once we found the thing that we want to explode, right, we're just exploding it. And we basically unwind the recursion until we found the left thing, and as we found the left thing, we start iterating to the rightmost thing to find the closest there. And as we found the right thing, we start iterating like in the opposite direction. Okay, so that's very interesting. So you go deep, you find the pair that you want to explode, and as you exploded it, you unwind the recursion and trying to sort of go in the opposite direction. So that creates like kind of a very interesting state machine in a sense, right? So there's several phases. Finding thing to explode, exploding, finding thing how to go, where to go left and where to go right, and then going left and right. So it's gonna be like this. All right, so I wonder how difficult that would be to pull off. Another thing that worries me is the tree is constantly modifying, right? The tree is constantly modifying, and how am I gonna convey that modification, right? Because, okay, splitting, if I'm splitting something, right? And what if I need to split the root, right? What if the root requires splitting? Right, so that means I need to return the new root somehow, right? I need to return the new root somehow, and that means the whole algorithm has to be around the fact that something can be replaced at any point, right? So something can be replaced at any point, which actually wastes the return value for very useful information like whether the split has occurred at all, right? So because you can have something like occurred, right? So because this is the information that this thing should return. It should return the potential new tree, right? Potential new tree, and whether the split has occurred or not. Right, and for the reduced tree, for the explosion, right? You have to return even more information, right? So you have to return even more information. That is a very cool problem. I really like that. So this is actually very interesting. So yeah, let me actually think a little bit and make a cup of tea. And after I make a cup of tea, we're gonna continue try to come up with something. All right. So while I was making a cup of tea, I think I've got a couple of ideas. Right. So let me try to see that. So essentially, we can have different situations, I suppose, right? So imagine that this is the pair that we want to explode, right? So we came to that pair in one of the ways, right? So let's assume that it was the left pair of that subtree, and that one was basically the right pair of that subtree. So they all usually have something there, like so. Okay, so essentially we can have two functions, right? Let me actually call them somehow. I'm not sure what going to be the signatures, but we can do something like shard left, right, node root. So this is one, and shard right. So essentially the point of that function is starting from a particular tree, just go always rightwise until you find some sort of it's not necessarily going to be, yeah, always go rightwise until you find a number, but you can also go to the left, right? And essentially, once you determined that you need to explode this thing, right, you need to keep track of these two nodes, right? I think I need to some sort of like a smoother, these two nodes, right? And for these two nodes, you'd have to call shard right, right, and it will basically will try to traverse it like rightwise, always until it finds the number. And for this one, you wanna do shard left, and it's gonna traverse it leftwise until it finds the number, essentially. Interestingly enough, if this thing does not have anything, it cannot have anything. I think it should have like something always. Yeah, as I already said, there is a very interesting property of that tree is that if you have one thing, you always have the another one. If you have left, you always have right, and if you have right, you always have left. It's just like, it's the law. Right, and because of that, it will work. So if you keep track of these two things, it is relatively easy. So this is one case. And I suppose another thing that we can do, we can consider another case, right, when we have something like this. Right. When we have something like this and we are about to explode this stuff. So this is another case, right? So for these things, we also have to call like shard right and shard left. And there could be another case, I suppose, right? Something like this, right? Something like this. If we have this sort of case, right? If we have this sort of case, we already by definition don't have the right number. Though one of the examples actually a little bit confusing to me. Okay, so that's fine. That's fine. I think everything's fine. All right, so essentially what we need to do, we need to keep track of the last two nodes that we visited. So that's kind of the problem here, last two nodes. So we have to have like a trail of these three things. And once we have that, it is actually relatively easy to do the shard explosion, right? So we only care about like these two situations. For this situation, we only have to do something like shard left, right? So we have to shard right. Actually, we have to traverse it like the rightmost. So, and for this situation, right? For this situation, there's also not much to do except go and shard left, right? For this one. So there's like 4 situations in here, at least. And I wonder if implementing things like that is going to bite me in the ass in the future, right? Because there's also part 2. And the question is like, what could happen in a part 2? Maybe in a part 2, they introduce a rule where doing this kind of stuff on these kind of trees is even more complicated than that. So that's a good question. That's a good question. So what I'm thinking is we can literally like check all of the 4 cases in here, right? So we start traversing from here, we start traversing from the root, and we first check this case and we make sure that this thing is explodable, right? So after that we want to check this case. So this has to be the first case if we traverse in leftmost. This one has to be the second one, right? I just drew them in a weird order. Right, then this has to be the third one, and this is going to be the fourth one. Right, so yep, something like this. All right, I want to try to implement that. I wonder, like, it doesn't sound too terribly bad implementing this thing, but I'm just afraid that if I'm going to implement that, the part 2 is going to bite me in the ass by introducing something that is even more difficult to implement than this. So I can just try to spend some time, but it could end up being a waste of time. So you see what I mean? You see what I mean? It's just like, okay. Let's give it a try. Sounds very interesting. So maybe we're going to implement shard left. And the point of shard left is essentially just always go leftwise, right? So always go leftwise and try to find a number, right? If you have root left, that means you have something. Right, and actually this thing has to accept a number that you want to add there, right? So I64n. And if we don't have anything, we are a number, and essentially what we're doing, we're just taking the value and adding n, that's it, and we unwind the recursion. So if we do have something, right, so we first go to the left, right, we first go to the left, root left. And interestingly enough, we shouldn't go to the right if we found the number, right? We shouldn't go to the right. So let me think. So maybe we're gonna return a boolean that sort of indicates this information, right? If not shard left, shard right, shard left. So we keep doing that. This is gonna be right. There we go. And on all of these things, we have to actually pass n, of course. So the thing about shard right is it's literally the same function. It's just like does that in a different order. Right. So root left. Might as well actually use root right for the consistency, even though it doesn't really matter for this specific case. And then I just return true, right? So this is going to be true. And if not, oh, this one has to be boolean. Shard right, so we always go to the right one. Root right, and if it's not available there, then at some point we will have to go to the left one. So my brain keep merging together words root and right. Root. That's what it's doing. So it has to be right, of course. Almost made a terrible mistake. Terrible mistake. Okay, so everything seems to be compiling. Control flow may reach. Well, this one is interesting. So if none of these things has happened, but otherwise, you can just return true, right? So it's more of like a short-circuiting situation, right? So if we supported short-circuiting, it could be left or right. I think that's what you can do. That's pretty cool. Right. So a good example of short-circuiting, but I don't remember if TempleOS supports it. As a matter of fact, like last time I checked, I wasn't 100% sure. TempleOS short circuit. How do you spell circuit? I don't remember. Why Google is so terrible. I'm not asking about freaking Linux. I don't give a shit about Linux. Okay, so TempleOS. Actually, I should have actually Googled HolyC. Short circuiting. Language design and analysis. Okay, so oh boy, it's so slow. Short, maybe syntactically shortened. Okay. Don't remember. Okay, whatever. Does not matter. Does not matter. So might as well actually do something like this to simplify the whole thing. And I really like that, like I have a compiler that does the control flow analysis, right? So I don't have to worry about it too much. Short left, short right. So and take a look at this thing and use parameters. That's fine. Control flow. I'm gonna return the root. Return the root, and there we go. Cool. So now let's try to do the explode. Right, let's try to do the explode. Explode. Explode, 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 explode. So since the level, so how do we even do that? Let me see. If any pair is netted inside 4 pairs. This one is interesting. Inside 4 pairs. So not bigger, but exactly 4. Not bigger, but exactly 4. Cool. That is actually cool. So that means that explode doesn't really need to return the new tree, because the root is never going to be like modified or anything like that. So essentially, if any pair, so maybe we can take a look at that stuff. So this pair is inside of like 1, 2, and there's more 2 pairs somewhere here, right? So there's more 2 pairs somewhere here, something like that. So that's cool. So we do explode, and we might as well also keep track of the level. Right, so at which level we're doing this stuff. So, all right. So then when we are exploding, so I start from root, so that means the level is 0. So the next thing is inside of 1. The next thing is inside of 2, 3, right? So this is the 3 of these things. And then here is the 4th one. So if this is a pair, at this depth, it has to be exploded, right? And so we are around here, right? We are around here because we want to keep track of the last 3 things in here, right? We want to keep track of the last 3 things. So that means the level at this point is going to be equal to 2, right? So there's 1, so this is the first level, and there is a 2, right? So this is the second level. So we only care if the level is equal to 2, right? So we can do something like if level less than 2, right? So this is one thing. If level equal to, this is another thing. Otherwise, we want to go out of the recursion, right? Because like there's no much sense to go deeper because this thing didn't say that we need to go deeper, right? So we can do something like that. So, and if we are less than level 2, we can just continue doing explode, explode root, actually left, and level +1. Interestingly enough, if the left one exploded, there's no point in continuing doing this entire thing. So I might as well actually return boolean, and for this entire thing, I can just return false. So can it be even deeper? 1, 2, 3, 4. If it's inside of 4, I'm just trying to find a trick. nested inside of 4 pairs. Okay, so I think it has to be exactly. Okay, so and if this thing didn't explode, we return explode root right level +1. There we go. If level is exactly 2, this is where it gets very, very interesting. Right. This is very where it gets very interesting. So we have to check 4 cases. This is going to be our first case. So we might as well actually have something like node A and node B. Right. So 1, 2, 3, 4. Cool. So the first case is going to be root left, right? The first case is going to be root left. Interestingly, maybe we could have separate cases, separate functions for all of those cases, if you know what I'm talking about. Okay, so something like explode case. I can actually try to do this try explode, because it does not guarantee that something is going to be exploded. Right, we try to explode. And here we actually do explode cases. Explode case 1, we provide the root, and we don't really care about the level. Right, and here we can also say try explode case 1, right, so this is going to be that. If it worked, if it didn't work, we want to go a little bit deeper, right? Try case. This one is interesting. If it succeeded, return true. Try explode case 2. True. So might as well just do things like that. I want to like simplify the whole thing, because I just like don't want to look at very dense code, if you know what I'm talking about. So case 3 and case 4. Right. So that's what we're doing in here. That's what we're doing in here. Explode case 1. Okay, this one is interesting. Bool explode case 1, we provide the root. And let me see. For the case 1, we need to have... also, I keep forgetting that there is a very important thing in here, right? So if root equal to null, it's a straight up return false, right? It's a straight up return false. Okay. Case 1, left, you have left, right? You have left. Not equal null. And man, I need to double check if there is short circuiting in TempleOS. This is very important, because with short circuiting, this entire logic is going to be a piece of cake. But I'm still not sure, because I'm just afraid that the lack of short circuiting will screw me really, really badly. Okay, so let me see. ed short HC. This time I'm not gonna look into the assembly. I'm gonna just try to like code, right? So we have a boolean and foo, and we're gonna have some sort of like side effects, right? So this is the foo, and this one is gonna be false. This one is going to be false, and then we're gonna have bar, which is bar return false, right? And in this particular case, if I do foo or bar, it's going to say foo bar. I actually have to put like a new lines in here, right? So it said foo bar, but if I replace that with and, it should say only foo. It said foo bar. Look at that. It said foo bar. This is actually so sad. Terry, why would you do that? This is such a convenient feature. Like, it could have like Yeah, so there is 100% no short circuiting, right? Because in this case, it does false, right? So full evaluates to false, and the entire thing is just considered to be false, so there's no need to evaluate anything else. Yeah, there's no short circuiting in Temple OS, and it's really, really sad. Okay, so let me see. AoC. So we have to suffer, apparently. I didn't see any other option. Just suffer. That's the point of the challenge. Home AoC 18. Okay, so where is that? So try explode case that. Okay. So we can do something like this. If leftmost is equal 0, this is straight up return false, right? If root left null, straight up return false. Cool. So this is how we achieve the short circuiting. So here's A, and here is B. So, and I can do something like root left. Right? Might as well put it in here. And then B is essentially A left. Might as well actually, like for the consistency, do something like this. Cool. So we have A and B, right? And I know that B has to be a pair, right? So it has to be a pair. So B has left. If it has this thing equal to null, it's a straight up false, right? So this is a straight up false. If it has the right thing equal to null, it is straight up false. So after that, we can check if left value equal to not equal to null, that is also false, right? Equal to null. So it's basically the number, right? It's basically the number. And essentially here, right, not equal null, it is also false because it has to be equal null. So there we go. So we have this case checked, and essentially, let me quickly do that. So this is A and this is B. Right, we are exploding B. Right, we are just exploding B. Root left is null, bad, saving it. A left, null, bad, go away. So B left, null, bad. B left, not null. That means it is not a number, right? It is not a number, it's also bad. So both of these things have to be numbers. So essentially, I need to have something like I64 X and Y. And essentially, this is what I'm trying to achieve. So left has to have a value. I could have actually come up with a more like explicit way of doing that, but it is what it is. Sorry. So this is going to be Y. X and Y. Interestingly, there is no left value anyway, right? There is no left value anyway. So the only thing I need to do is basically shard left and go to the right. Shard left, A right, and the value is Y. There we go. So, and after that I can just return true. There we go. So this is a single case, if I understand everything correctly. This is a single case, right? 3 more to go. 3 more to go. Maybe there is a way better way to do that, but I'm too dumb to come up with that way. I'm really sorry. And again, I wish there was like some sort of a thing. So the only thing I really don't like, I still don't like that I don't have a consistent way to determine whether this is a number or this is a pair, which kind of like pisses me off a little bit. I can add more information there, some sort of a boolean or something like that, but nah, doesn't sound very good. So though numbers here are very, very small, right? So they are in fact very, very small. So I could have like split value into two values. One indicates that it's a number or not, and then the other one contains the value. I could do that. But why would I do that? Anyway, so I think this is more or less reliable way of doing that, but it's just like very error prone. So yeah. Okay, root left does exist. If it doesn't exist, it will go away. And left does exist. Okay, so this is the first case. Then we're looking at B. B left. Though I could probably extract this pattern into some sort of a function, which is a very interesting idea. Right, so I don't know how to call that function, but I can accept root in here. I could accept root in here. And then I could accept a number, pointed to a number, and essentially just check it myself. If root left is does exist, I just return false. If it doesn't exist, I just return true, but I also set x to the value, right? And this is very interesting because then I can do something like, let's call it something like try get value, right? Try get value, and then I can do try get value b left x, and if this thing fails, if I couldn't get the value, instantly return false. This is a bad case. The second one is going to be like this. There we go. And that compresses this entire thing. All right, that is very cool. I really like that. Try get value. We could also do something like if root only if root, and then return false. So could be compressed somehow, I suppose. Right, so we can put this thing in here. Can put this thing in here. If root and not root, do that. In any other case, don't do anything. Okay. Interestingly enough, can we have something like try get left as well? That is a very interesting idea. So if I keep doing that, try get left and try get right, node root, node left, so literally the same thing. If it does exist, we just do left and return true. Okay, and then I can have something like right, and it's gonna be something like this. Try get left and try get right. So, and essentially I can do things now the following way. If try get left root a, return false. Try get left a but b, return false. Cool. So then I'm getting b. But is that the correct thing to do? That's very, very interesting. So I'm getting b, but then so I'm trying to get the left one. Left one exists. The right one, I try to get that one. So then I can get the value, but we also check for... I think it's going to be fine. So this is the explode case one. This is the explode case one. Easy. Okay, so that's actually pretty easy. Okay. I wonder if I can flatten some of these things. If not root, return false. If not root left, return false. Otherwise, this control. So if not root, if left, return false. Otherwise that. Cool. So then for the left one, if not left, blah blah, left, left, and replace left, right. Okay, so this is the things we have, right? So we can, yeah. So it's plot case, try to get left, blah blah blah. So the second one is interesting, right? So that makes it a little bit easier for us to work with this thing. The second case, we are going to the left, get left, but this time we're going to the right, right? So it becomes right. After that, so left and then the right. After that, we trying to get the values, x and y. And this time, by the way, we have everything. We have everything. So I need to actually mark this stuff. So this is the root. This is A and this is B, right? So that means now I need to do shard right on A left, shard right on A left, and I have to add X in there, right? And then I have to do shard left on root right, right, and add Y in there. So that's basically what we have in here. So this is a case 2. Case case 3. So this is going to be the case 3. So for the case 3, we go right, left. We go right, left. Go right, left, and then we take that. Yet again, this is a root A, B. So, and in that case, I do shard right, root left, right, and shard left, A right. Yeah, so that's basically what we're doing. So this is a case 3. This is a case 3. And then we can have case 4. Case 4. So in the case 4, we do right, right. So in all of these cases, it's just like right, right. Right, right. And in that case, what do we need? We only need to go into root, root A left, shard right, A left, shard right. So yes, that's the 4 cases, I think. That's basically 4 cases. Let's try to compile this entire shit. It's probably not going to compile. So blasphemy, sh. Right, so what do we have in here? Try explode. Okay, so that's fine. What else do we have in here? A and B. Unused variables, we don't need them. That's precisely why. Okay, so this is the thing. So maybe we can also do a similar thing, like root that. If level is less, we just continue doing this thing. If level is exactly equal, we just do that. If it happens to be greater, well, there's no point in continuing, so this is straight up false. Split, we're not doing split yet, so might as well just like remove that. Magnitude, I don't know, I can cast this thing by 64, I just don't want this thing to complain at me. But yeah, whatever. Okay, this seems to be working more or less. This is a very cumbersome way of doing that, so I do not disagree with that. It is in fact a very cumbersome way of doing that, and we will need to test those things somehow. So let me see. I want to double check everything first of all. So shard left, so that means we always go leftwise, leftmost. And it indicates whether it happened or not, right? But doesn't really need to. I don't think so. No, it doesn't need to. So we're just sending a shard there, and we forget about it, whether it happened at all or not. Because I think if you go there, it's always going to reach something. It's always going to reach something. At least I think so, but it might be terribly wrong. So because of that, I think I can simplify shard left and shard right dramatically by not having a boolean, right? So just send it there and forget about it. Okay, so you don't have to return anything, and you can just do it like that. Okay, so shard right, I'm just gonna do it like that. Well, no, we need that. I'm an idiot. Okay, so I'm already going crazy. Boolean. So it is important, right? Because, yeah, you need to be able to find that. But then we don't really need that information that much. Okay, so let me try. So let me try a different case. Like, I'm really paranoid that I made a mistake somewhere. All right, so I don't like that I don't check for root in here, right? I really don't like that. So I'm not even streaming, but Lindra Braga, thank you so much for 13 months of Twitch Prime subscription. Thank you. Okay, so if not root, right? If we don't have a root, just return false instantly, and we can put this thing here as well. All right, that makes sense. So we double checked all of the cases in here because that's the assertion. Get value, no root, no value. If you have left, that means it's not a value. Otherwise, it's a value. If you don't have a root, don't have a left, blah blah. If you have left, we return that. No left, no right. Okay. A and B, left, 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 right. So only to the right case. Left, right, A, shard right, A left, root right, shard left. Makes sense. Right, left, right, left. That means right, right, left. Shard left goes to the right, A, right, shard left. And then we have right, right. And we only can go I left, shard right. Cool. So, yes. Yes. Let's test that. So I'm gonna go into the sample, right? And I'm gonna actually copy paste all of these things. So I'm gonna start with that stuff, and there we go. So what we're doing in here is essentially I'm going to be parsing the tree, right? I'm parsing the tree and I want to print that tree right away. Print tree arg. So that's basically what I want in here. Blasphemy, this is the root. Well, I mean, I don't care about that. No matching function. Are you sure about that, buddy? Okay, so but I provided arg. Oh, it doesn't have to be pointer. I see. All right, so what if I also run it right away? So that gave me this thing. So let's not print part 1 yet. It's not really important. And the thing I want to do now, I want to explode the tree, right? Why? Oh, it's a try explode. Try explode, and I'm going to provide the arg. And if we successfully exploded it, we're going to say something like print exploded, like this. Then I'm going to print the tree one more time, and then I'm going to print the new line like this. So in here, if it didn't explode, we're going to say could not explode, and we still can print this thing. So it kind of, yeah, we can move that stuff away from this, right. So try to explode, exploded, could not explode, and let's just see how exactly it is exploded. And of course, I forgot to provide the new line, print new line, right. Okay, so could not explode, and it didn't do anything. It kind of tried. Oh, okay, that's really weird. That is really weird. Why? Like it tried to do thing, but it at the same time it said it didn't. Because why? Try explode later, explode right. Okay, so I also can see that I forgot a very important thing in here. That is very important. I forgot to set B to null, essentially, in all of the cases, by the way. Right, in all of the cases. So we send in the shards. Yeah, this is very important. Oh my god, this is so annoying. So this the whole process is probably not gonna work. Right, so yeah. Fuck. So when I'm doing this thing, right, I'm sending all of that away from B. I'm sending all of that away from B, so that should be fine. So one of the things that I probably have to do now, yet again, right. A left should be alloc, node alloc. Right. Yeah, there we go. So A left should be node alloc, because we need to set it to 0, and to set it to 0, you just need to 0 initialize thing. Yeah, so that's fine. Okay, so it's basically left here. Okay. The case 2 is left, right, left, right. So that means for the case 2, I have to set right to null. Right, so I'm gonna set right to null. So that way we're kind of leaking the node, but that is fine. Just buy more RAM. It's 2021. Come on, bro. So I guess that's what we have in here. Okay, so that kind of worked, but at the same time it informed us that this thing didn't explode, which is really strange. I don't like that. Right? Why it did the thing and then it informed that it couldn't do the thing? That is really strange. Okay. So exploded, couldn't explode. Might as well actually put something like this. Right, and I think it did it correctly. Like, right, so it's 0, 2, 3. But why didn't say could not explode? This is so annoying. So at which point it could say something like that? Right, I try to explode, right? So if it's null, I just go away, and if it's less, I continue. I try to explode on the left side. If I couldn't explode, I try the right. All right. So if the level becomes 2, that means the next, 2 are going to be right there. I try the case 1. So in the case 1, if everything went okay, this thing is going to return true, meaning that I'm going to instantly return true. If any of these cases like succeed, it should be fine. Right, it should be definitely fine. So I'm really confused. What the fuck? So it's only if it failed. Okay, so there's probably something here, so let's try to see. I'm gonna print try case 1. So there's a case 1, then this is a case 2. I just want to see what's happening in there, and then the case 3, and then the case 4. Right, so here's the case 2, case 3, case 4. Okay, so it hit the tries case 1. I can clearly see that. It hit that thing. And if I put this thing in here, right, if I put this thing in here, we can clearly see that it returned true, right? It in fact returned true. And in here, if this thing returns true, I would be returning true as well. Oh, okay, I see. So because of that, I think I'm gonna do it like this, because the the control flow analysis of the compiler actually didn't help me to catch this one. Yeah, exploded, and it exploded in the test case 1. Okay, so that's cool. All right. So maybe did not explode. So, and in here we can also print like a huge line between all of them, right? Just to see, because I'm going to be adding all of that stuff in there. Try explode case 10, and let's just remove that. All right, so we have exploded, and let's start adding the rest of the things, right? So we're going to put this thing in here, right? So now we have that. Yeah, that was interesting, and I think it did it correctly. Yes, it did it correctly. So let me remove all that logging. Print. Try. Okay. So let me see. Exploded, and if I try this thing, sample. All right, it exploded, and it didn't do shit, bruv. I think I made a mistake. Okay. So that means I need to go higher. That means I need to go higher. I see. So this case is even more complicated than I thought. Yeah, so it's not gonna work. So you need a completely different data structure. I see. Let me think about that. While I was making a cup of tea, I didn't finish making cup of tea, so I'll go back to the break again. While I was making cup of tea, I got an interesting idea. So if you like literally consider the string, right? If you have something like that, implementing the explode, just interpreting tree as a string is relatively easy if you think about that, right? Because yeah, look, you can just iterate the characters, or rather, let's call them tokens, right? You can iterate tokens from left to right, and every time you encounter open bracket, you increment some sort of like a level counter by 1, right? And if you encounter the close bracket, you decrement it by 2, right? And once your level reaches 4 and you see open bracket, you can look at the next 4 tokens, right? And you can see that these 2 tokens are numbers, and that's the pair you have to explode. And then exploding this entire thing is relatively easy. You replace these 4 sequence of tokens with 0, and you go to the right and find the first number token, and then go to the left and find a first left token. Right, so if you look at this thing as tokens, it is rather simple, isn't it? Right, and splitting is also rather simple, right? So you have to just take one thing that is bigger than 10, and you just replace it with this sequence of tokens. It's going to be 6 and 6, right? But you need to have an ability to concatenate the strings of tokens that way, right? So, and adding 2 numbers together is also simple. You have these 2 numbers, right? You take these 2 sequence of tokens, right? You add this token here, this token here, and this token here, right? So you don't even need to represent this as a tree. You can just work on a sequence of tokens, and you need an ability to concatenate those tokens. What if we implement something like that? That would be actually kind of cool. So maybe we can even get rid of the comma token, right? So let me actually replace this entire thing with just space, right? So there's no comma token. There's only open and close and the number. That's it. So we have only these tokens. How are we gonna do that? How are we gonna do that? That's a very good question. So we can represent each individual token as a single number, right? So it's gonna be maybe I64. Let's actually do something like type def I64 token, right? And then you just have an array of tokens. You just have an array of tokens of a certain capacity or whatnot. And then you will need a couple of operations that essentially concatenate two sequence of tokens, right? So maybe something like token cat. It can basically accepts the base, right? Maybe let's actually call it tokens append, all right? And essentially it will just write a particular sequence of tokens into there, so that way you can concatenate things together. Once you have like this representation and these operations, implementing all of that becomes rather trivial, because if you're iterating from left to right, you're basically traversing the tree leftmost anyway, right? Yeah, you do. In fact, you do, right? So because leftmost traversal of the tree is basically iterating its nodes, its leaf nodes from left to right. And the rightmost is basically iterating them from right to left. You don't need a freaking tree. You can just like have a sequence of tokens and operations and a sequence of tokens. My God. But I still haven't finished making my tea, so just a second. I'm gonna go make a tea. Okay, let's go ahead and implement that. So yeah, we essentially need to scrap this entire idea, right? I don't think it is a good idea anyway, so let's just like remove everything. I cannot have a comfortable workspace for some reason. I need to invest into a better like table or something. So we're gonna remove that, reduce short left. None of that is like important. It's just too much code. When you pick a wrong data structure, you just write a lot of code to compensate that. Okay, so as I already said, I want to like have a token, which is basically I64, right? So we can just have it as I64. And then we're gonna have like a predefined token values, right? How do we're going to indicate the open bracket? I think the easiest way to indicate an open bracket is probably to use negative numbers, because the values of the pairs cannot be negative, right? So token open, right? So this one's going to be -1, and token close is going to be -2, right? So this is going to be like the values. So let's also define something like token capacity. Let's allocate like, well, to be fair, it is very interesting because we'll probably need several areas with tokens, right? We'll see actually. So let's actually have a token capacity for now, and 124. So, and what I want to have in here is some sort of a function that prints tokens, right? So we're going to accept the tokens, and also token size, there we go. And then I64i, then for I equal 0 less than token sz, right, like so, plus I. And here we're going to have an interesting thing. We're going to switch switch upon this stuff, and we're switching upon the tokens I. So here we have a case of token open. In that case, we just print this thing, right? So we also have to break in here. Then we have a token close. So then we close the entire thing, break, and for the default one, we're printing the number. Tokens I, right? If it's not negative, it represents basically itself. So that's basically what it does. And then, do we need anything else? I didn't think so. So the way we're gonna parse the tokens, let me see. So I'm gonna introduce something like U8, U0 parse tokens, right? So parse tokens, we're gonna provide the string view. We're gonna, for now, maybe parse everything in here, right? And Where I'm going to be putting all that? That's a good question. So I need some sort of I64 tokens size, right? So token size. By the way, token capacity. Why didn't I use token capacity? There we go. So here's the token size, and I think it has to be a pointer because we're going to be just incrementing this entire stuff. And are we going to be doing that into here? Right? Probably. Tokens. Might as well have a token capacity, I64 token capacity, so we know how much we have, and then we're also going to pass this thing, which is going to be incremented, right? All right, so we're going to start with the token size equals 0, maybe, right? And we also need something like this for, you know what, probably not, because we can do something like this, while SV size is greater than 0, right, when it's greater than 0. So switch, switch upon SV begin, and if this entire thing starts with open bracket, we're doing the following thing. Tokens, tokens. So I have an interesting idea. We might actually do something like this. If tokens token size if tokens size is greater or equal to tokens capacity, something like this, yeah. Actually less. We're gonna do token size plus, and this is gonna be equal to token open break. Similarly, token close. Next one is interesting. So we have a default. So if I was using some language that supports like easy string concatenation and garbage collector, I probably wouldn't even convert that. I would probably do all of that on the level of strings. But here I'm in TupleOS, so I have to do that. So the next thing, I probably now need to allocate a variable, right? No, I don't. I can just do str to I64. I provide the SV, and I can just do tokens SZ++. There we go. So that's literally it. That is literally it. So because of that, maybe we can make token size returnable. I think that's a good idea. Cool. So it will just return you how much it allocated. It read, so it's going to be token size. And then you can see if it actually filled everything or not. That's very cool. That is very, very cool. Though it also chops the tokens, right? So we want to actually call it chop tokens. Chop tokens, because usually when a string, when a function modifies string view, I prefer to call such functions chop. So chop sort of indicates that, yeah, that modifies string view. Okay, so here, and this is why chop by delimiter, it modifies the string. We don't need to have a parse or anything like that. All of that is not needed. So here we have a line. And what I need to do, I need to chop tokens, right? So I need to chop tokens, and then I'll need to print the tokens. Print tokens. So we're chopping tokens out of the line. We're providing the tokens and the token capacity. And then, so this is the size, which I probably want to keep, tokens size. Right. I64 token size, and then what I want to bring in here is just the token size. There we go. Cool. So if I now try to compile the entire thing, it does not compile because why? Thank you so much, C++ compiler. Very cool. I think it has to be SV chop I64. Right. I almost pressed F5 because F5 is a compilation in TempleOS. Right. Because, yeah. No matching function. I wonder why. Oh, because I have to do it like that, of course. I wonder if it's gonna work properly. Is it gonna work properly? No patching function. So is it called something different? I think I forgot how it's called. I64. SV chop I64. Okay, so that. Oh, because it's already a pointer. Okay, thank you. So this is one of the shit that HolyC really sucks at. Print tokens, token side. So we don't need that stuff anymore. Semicolon. Anything else? User of undeclared identifier token, but I defined it tokens. All right, so tokens capacity. Did I not? Yeah, I called it token capacity. Okay. I know what happened. I need to do SV chop left after that. Alright, so it's gonna be like this. Alright. Cool. Are you serious? This is supposed to be a strongly typed shit. What the fuck is going on? Alright, that is... Okay, so I think it consumed everything for whatever reason. SV begin, and I'm chopping left, and when I'm chopping left, I'm supposed to be chopping a single character out of that. Oh, yeah, I know. So if I have a number, another interesting thing, after that I have to chop the comma. Okay, skip this, skip this, skip this. There we go. Now we're talking. Now we are flipping talking. So for the numbers, I would like to maybe put some spaces around them, just to indicate what the fuck is going on. Is that a correct shit? I don't think it is a rather correct shit, but maybe it is. So if I take a look at the sample input, right? So this is the sample input. Yeah, there's something wrong in here. As you can see, there's zeros. All of a sudden zeros. Oh, this is because I'm an idiot. Okay, maybe, but who knows? You never know. Because we have several of them. So if I print a new line afterwards, right? If I print a new line afterwards, here they are. But I think we fucked up the closing parents. I think somewhere. I think we fucked up the closing parents somewhere, but it's kind of really weird. So let me see. So this is the sample. Here's the... Yeah, it doesn't parse closing ones for whatever fucking reason. Oof. Oh yeah, I see. So maybe instead of doing it like that, if I encounter like this thing, I'm gonna just skip it. I think that's the safest thing to do in here, just skip it. Just skip it. Yeah, there we go. So that makes a little bit more sense. So these are the tokens that we've got. These are the tokens, and they do look like tokens, I would even say, right? So they are in fact tokens. So now, what we're gonna have in here, we need to be able to explode the token somehow, right? So chop tokens, print tokens. Let's do explode tokens. We also want to return boolean to indicate whether it was successful or not. So here we have tokens and the token size, right? Maybe this one is going to be like a source tokens, because I think we're going to be copying them into like a destination tokens every time we explode them. So this is going to be a DST. I'm not even going to call it SRC and DST, but according to the like Intel convention, usually DST goes here. So I don't know. So here we might have DST capacity, so how much we've got, and SRC we may have actually SRC size, right? So SRC size, how much stuff we've got in there. How much stuff we've got in there. And Yisu, kawai freaking this one. We have a DST capacity, but we also want to be able to have a DST size, right? If that makes any sense. Not really. So if we're now operating at the level of the tokens, right? We're now operating at the level of the tokens. We just want to find the exploding thing, right? And essentially, we want to take this entire thing and shift it by 3 tokens to the right. Right, that's what we want to do. So then we can replace the other token with like 0. And throughout the entire process, we still know where everything is located, right? So we still know where everything is located. So then we can go left and right, trying to send the shards. So, and here is the thing. I didn't think we need DST. Because since every time we explode, the sequence of tokens shrinks, that means we're not going to overflow or anything, right? So we're not going to overflow. So we only need to shift things around. So this is the size, but the size might be modified. The size might be modified, and this is something that we have to deal with. So now, do I want to actually pass the size by a pointer and let the explode tokens to modify the size, or do I want to actually return a new size? And then probably if I'm modifying everything in place, I probably want to actually return that size. That makes a lot of sense to me, I guess. I guess that makes a lot of sense to me. So, all right, let's go ahead and do that. So I64I4 I equals 0. Less than SRC size. It's a very interesting operator in here, right? Plus I. Okay. So, and we need to maintain the level, right? Level initially is going to be 0. If we encounter something like SRC I equal token open, right? So this is the open token. And so you can have several situations in here. You encounter open token and level is equal exactly 4. That means you have to do the explosion, right? To do explode. Otherwise, what we're going to do in here, we just increment the level by 1. Otherwise, if we encounter SRCI equal token close, we're going to decrement the level. We decremented the level. Otherwise, if we encounter just a number, we're just ignoring that stuff. So it feels like I should have used switch case. So switch SRCI, and in here we have this sort of situation. Case. Else break, right? So then case, then that, close is going to be that, this is break, and then we need to have a default. In case of a default, I think we can say that we're doing nothing, right? So, and okay, when we went through the entire thing and nothing happened, we just returned false, we didn't explode. We didn't find anything to explode. So here, we're gonna return true after we exploded everything. So there is actually a lot of other things, right? So first of all, we are here, and we need to take a look at the first 3 things in here, right? So these things. If I plus 3 is still less than SRC size, right? And there's no short circuit in here, so we have to do something like this. I plus 3 and SRC and src I plus 1 equal greater or equal than 0, and src I plus 2 greater or equal than 0, and src plus 3 is equal to token close. And I think at this point it's kind of pointless to check this condition, right? If the data is correct, it will never gonna be false, right? So it's kind of pointless to check for that, but it's kind of assumed, right? So it's sort of like assumed. And when something is assumed, we usually use assert, but I don't know how to use asserts in Temple OS, so I'm gonna just like do it like that. So this is what assumed in here, right? So, and this is where we have to do the explosion, the actual explosion. If this is not true, right, if this is not true, we just continue. We just, you know, keep incrementing the level, you know, keep incrementing the level. There we go. Just keep incrementing the level. And this is where we have to do all of that stuff, right? So, essentially, I need to move like everything from here to here, and I wonder if there's something like memory move in there, or I can implement all of that myself. Not that big of a deal. But first of all, I need to save the values, right? So I discovered that this is fine, and the next thing I want to do, I want to actually save those values, right? So this is going to be A, and this is going to be B. There we go. So this is going to be A, and this is going to be B. A and B. So also, maybe I want to have something like J, right? And I'm going to probably just iterate J equal I. 1, 2, 3, 4, right? Plus 4, J less than src size plus J, right? And essentially what I want to do, I just want to do src I. I guess we wanna do something like this, where I kind of start from, I don't know, from 0, and while I plus 4 plus J is less than this entire size. So then I can just do I plus J equal src I for J. There we go, log for J. Anyway, so cool, and that's how I move all of that, right? So that's how I move all of that. So after that, we probably want to decrement. Not really. Not really. So it's going to be 0, 1, 2, 3, 4. And I need to move all of that kind of like here. Right. So it's plus 4, but I'm moving that into like 1. So that means I need to have set that slightly to here. Right. I hope it's not going to cause any problems, but we'll see. We'll see. The winner gets T, that's for sure. So it is accessible, so we'll see. Like, it's kind of difficult to wrap my head around that, but that's fine. That's totally fine. Okay. So, and one of the things I want to do in here is essentially I also want to replace src I with just 0, right? So it becomes the exploded, like leftover of the explosion. So now we've done that. I need to decrement the size. 1, 2, 3. I think I need to just decrement it by 3, essentially, right? Because I removed like 3 tokens out of that. And after that, we probably want to do the following thing. We're going to do j equal I minus 1 until j is greater or equal than 0, right? and plus plus I, and what we actually plus plus minus minus j, I'm sorry. And if srcj is greater or equal than 0, right, we simply do srcj plus a, right, so this is plus a, and we break out of that. So this is the left shard. Then we can have the right shard where we do I plus 1, and this thing is just src size plus plus, and if it's that, this is going to be the right shard. And there we go, we just exploded. So that's a little bit complicated, a little bit annoying, but not as annoying as dealing with the trees and shit, if you know what I'm talking about. It's not as annoying as dealing with trees and shit. Okay, so let's take a look at if it actually does things. So we want to explode the tokens, right? So we print the tokens, and let me see. So it's going to be that. If tokens, and then token size, if we explode it, we're going to say print exploded, right, with a new line. And maybe here we're going to say failed, right, failed. And then I want to print the tokens, right, so give me tokens size, there we go. Token size, and let me see, so it didn't compile because this is tokens, right? Okay, so, and it exploded into actually bigger shit than I expected, so, excuse me? What the fuck? Why did it become bigger? Why would it become bigger? Because I've not incremented, what the fuck? Excuse me? So, all right. So it said that exploded, but then we have. Oh, I think I'm an idiot. Okay, I'm sorry. It's a print new line, and I also want to actually separate by big new line, by big line here, just to see what's going on. Okay, so that exploded. I think. Did it? I don't think it did. So that should have... No, it did. It actually worked. The fuck? Okay. 7. And another one where we have like 6, 7, 0. It worked. I think it worked. Yes. So you can do it like that. I mean, yeah. So on the level of tokens, I think it's a bad idea. Actually, it's actually a pretty cool idea. So let me try the rest of the samples. Right, let me try the rest of the samples. We're gonna try that one. All right. And 8, then 9, 3, 2. Okay, that is easy. That is too freaking easy. Okay, so what about that stuff? Okay, 7, 0, 8. Okay, so that's easy. All right, so we implemented exploded. That's cool, and I'm super hungry, but it is what it is. Okay, so can I actually make it a little bit more compact? Probably. One thing I wanted to do, I wanted to check how it works on TempleOS because I haven't checked it for a while. So let me run AoC 2021. So it's a drive C, and in here I'm going to take a look at this stuff. So it's 18 and main.hc. So if I try to compile that, it works. Okay, so it works on TempleOS, so everything is compatible. Cool. So I so intuitively feel TempleOS that I can just like write HolyC and it just works automatically on TempleOS. Cool. All right. So what about splitting? So how can we split the thing? We're gonna just iterate to the right. All right. We're gonna just iterate to the right, and yep. And when we find something that is bigger than 10, we're gonna, you know, do that stuff. We're gonna we're gonna split it. Mount AoC 2021. All right. So and let me see. So I don't know what I'm doing. Home AoC 18 main.hc. So explode tokens. All right, then we're gonna have something like split tokens. All right, and split tokens accepts the tokens, right? Tokens, and it's probably gonna accept the token sizes, right? Token SZ, token SZ. But here is an interesting thing. Unlike explode, which reduces the amount of tokens, split tokens increases the amount of tokens, right? So so how are we going to convey that? So we're going to increment token size, but we also want to do something like I64 tokens capacity. We want to know what kind of capacity do we have in there, right? So will we be able to do that in place? Probably. So in case if we ran out of capacity, one thing we want to do in here is essentially just scream, right? So that's the only reason why we want to have a capacity in here, just to scream at the user. Anyway, so I64i for I equals 0, tokens z plus I if tokens I is greater or equal than 0. Actually, greater or equal than 10, right? So how did it say? 10 or greater. Okay, perfect. And then this is where we're going to do the split. This is where we're going to do the splitus. Bruv. So we can just put something there, I don't know. Where is the sample? Sample txt 1020, right? 1020, cool. So in here, we got that. So, and then I just want to see if tokens size. So how many tokens do we add in here? 5. So we add, in fact, this has to be the space, right? This is the space. We added 3 tokens. Okay, if size plus 3 is greater than tokens capacity, if it's greater than tokens capacity, we're gonna scream at the user. But we're not gonna do much else, I think. We can also return false just in case, right? Capacity overflow on split. Allocate more memory. Right, so this is a new line, and there we go. Also something like, I don't know, just to be sure. Okay, cool. So that's very important. Very, very important. Cool. So now we're going to be iterating to the right, I suppose, right? So we have to start iterating from the end and keep offsetting everything. So let me actually align all of the tokens together, right? So we can clearly see them, right? So these are all of the tokens. We can clearly see them. So this is 3 additional tokens. So what I have to do in here now is essentially take this token and move it to +3. 1, 2, 3. Yeah, I have to move it to +3. So I'm gonna start with for j equal to token size -1, j greater or equal to, I suppose I is greater than I, so we shouldn't go into I, that's for sure. So 1, 2, and then, yeah, it has to be greater than I, and then this is minus j. Minus j. So, and in here, while we're doing all of that, srcj plus 3 is going to be srcj. 1, 2, 3, so plus 3. So that's fine. Cool. So this allowed us to move things around, right? This allowed us to move things around. So after that, I need to do the following things. So tokens, well, it's not called src. Tokens. But my brain already decided that this thing is called src, so it's just like, yeah, there's nothing I can do about that. My brain has decided, my brain has made a decision, that's it. Token open, right, so this is going to be that. Then we're going to have tokens I plus 1, which is the number, right, which is the number, but we need to save that number. So let's actually do something like A, here's the J, and there we go. So A is going to be equal tokens I, so we're going to save that just in case. Just in case. So this is open, and this one goes rounded down, if I understand correctly, right? So we divide it by 2 and round it down. So in that case, it's just going to be that. Split, split, split. I don't see shit. Regular number, replace it with the pair, the left, okay, so in the right, up. Okay. So, and tokens I plus 2 is going to be equal to A plus 1 divided by 2, right? So that will turn it into rounded up, and then tokens I plus 3 is basically equal token close. There we go. So that's what we have in here, and that is literally it. After which we can just return true. So we split this entire thing, and then we can return false. There we go. So I think I successfully implemented that thing. So split tokens. Right. If I try to compile, I can't compile. Blasphemy sh, right? So we have that. Split tokens also accepts the capacity, tokens cap. Let me see. Okay, so this is the tokens capacity, and there we go. So everything seems to be compiling. What about this? What about this? And ooh, cool. Where's the rest of the tokens? The fuck? I think I know what the fuck is going on. So I forgot to just add 3 in there. I'm pretty sure that's what I forgot after we've done all of that. Right. So that's what we need to do. And there we go. So we managed to split that successfully. We managed to split that. Can I split that second time? That's a good question. Let me see. So this is the second time. So, and the second time we managed to split that too. What about the third time? The third time should tell me that, bruv, no, you can't do that, bruv. And it managed to do that. Well, equal to 10. Okay, fair enough. Fair enough. That means I can actually keep splitting this shit. There we go. Yeah, and that means on the 5th time, right, so this should not happen, failed. And it just says the same. Cool. So, but that's not the only operation that we want to perform, right? That's definitely not the only operation of our nation. So another thing we want to perform, we want to be able to add 2 numbers together, right? We want to add 2 numbers together. And that should be relatively easy, to be fair. So essentially, we're going to do add tokens, right? U0. So we're going to have tokens like A, maybe access, and then I64 access size, then token wise, then I64 wise size, and then we're going to have a destination, right? Some sort of a destination. But do we really need to do it that way? So that will require like having 3 of these things, right? 3 areas of the tokens, if you know. So let me see. Maybe we're going to accept it like this. So this is going to be the destination. This is destination size. And the destination size might be changed. I64, we're also going to keep track of the destination capacity, right? So, and then we're going to have the SRC and SRC size. And essentially, right, this is what we're going to do. So we need to make sure that if you do DST size plus SRC size, right, essentially we have a bunch of tokens like DST and SRC, right? What we need to do is concatenate them together. We're concatenating them together and wrapping them around with this shit. Easy. So essentially the final size is going to be DST size, SRC size plus 2 for the open and closed token, right? So that's basically what's going on in here. It also means that I have to shift the destination. Just keep shifting the destination. Right, and let me actually do something like this. If this thing is greater than DST capacity, right? Capacity overflow, right? Capacity overflow on add allocate more memory. So we know that this is going to happen. We kind of know this is going to happen. So the next thing is I want to move DSTs to the right a little bit. So it's going to be 6 I64 I. For I equal to 0, right? I less than, well, I mean, I have to iterate starting from probably DST size, right? So this is going to be DST size minus 1. Is that how I do that? Yes, DST size minus 1. And then greater or equal than 0, minus 1. So, and in here is just DST I, DST I plus 1 equal DST I. Right, so we're just like shifting everything. And after that, DST 0 is going to be equal token open. So we're opening the tokens. That's fine. So we're opening the tokens. After that, by the way, DST size should be a bit bigger. Right, so plus 1. So now we have that. And so then we just need to append all of the SRC tokens as well, right? So that's what we need to do. So let me go ahead and do that. For I equals 0, I less than SRC size plus I. So, and in here, what we're doing is essentially we take DST, DST size, right, DST size plus equal SRC I. So we keep appending this entire thing. We keep appending. And after that, we can do another thing in here, which is essentially just, you know, token close. Okay, so, all right. It's a bit complicated, but it's not as complicated as working directly with the trees. So, yeah, let's try to compile this entire thing. It does not work. DST SRC, aka long. So do you want me to do something like LL, or what the fuck do you want from me? Actually, okay, I see what you mean. All right, so, but we're not splitting anything. Okay, so let me take a look at the sample. And what I'm going to try to do is essentially just add things together. Maybe not. So let me try to just have 2 examples in here. And I'm going to just allocate 2 arenas for the tokens. So this is going to be tokens capacity. So let's call it maybe tokens 1 and tokens 2, right? So we have 2 of these things. We might actually allocate a little bit more just in case, like 2,000. Who knows? If something wrong happens, we can always, like, you know, allocate more. So what I'm doing in here, I'm chopping the line. So here's we chop in the line, and we have tokens 1 size and tokens 2 size. So that's important. So tokens 1. Let me remove all of that. So chop line, here is the first one, and then tokens 2. All right, and then we can do print tokens. This one is going to be tokens 1 tokens 1 as z, and this is going to be the second one. There we go. If I try to compile this entire thing, probably want to put some sort of a new line in here. So here's the second one. Cool. And the next thing I want to do, I want to add tokens, right? So let's add the tokens. Cool. So it's going to be token 1. Then the size of that is going to be token 1 SZ, tokens capacity. So this is the capacity. Then we do token 2 and token 2 size. There we go. After that, we want to try to print token 1. Okay, so let's see if it's going to work out well. It didn't even compile. So add tokens, what does it expect as the first thing? Token S. All right, so it's something like this. Token, another one. All right, so we managed to do that. Look at that. That's pretty cool. I think that's pretty cool. The final sum is something like this, and we also need to compute the magnitude, right? So, and the magnitude is something also with the nestiness, right? So to check whether the magnitude of pair is 3 times the magnitude of its left element plus 2 times the magnitude of its right element. The magnitude of a regular number is just number. Ooh, okay, so this one is interesting. So this requires some sort of a recursion then, which we can perform, right? It's not that big of a deal, but yeah, we can. So what's funny about this structure, what's funny about this sequence of token structure is that I still can traverse it recursively. Jesus Christ. I don't know how to speak English, I'm sorry. I should start speaking Russian at this point. Okay, so let's go, I suppose. Where's my sample txt? This is a very annoying problem. It's kind of fun though. I don't know, I kind of enjoy it. And I wonder if it's gonna explode really badly and it's gonna be super slow, but we'll see, The winner gets tea, that's for sure. So, and essentially, right, for the first one, we just want to remember the first one, right? So let me see. Boolean first. First. Oh, what? Nah. True. Okay. If first, what we just do, we just initialize token 1, right? Tokens 1. Though, I have an idea. What if I call this DST and I call this SRC? And then tokens, where are my tokens? I'm gonna call this DST and this is SRC. I think that's a cool idea, believe it or not. I do think so. So if the first we assign DST size, then DST, and there we go. So we've got the first one. If we've got the second one, what we have to do in here, we have to do that into SRC. Right, we have to do that into SRC, and then we have to add them together, right? So add tokens, we add in that shit together. So this becomes DST size that can be modified, then tokens capacity, right, tokens capacity, and then we provide the SRC and then SRC size. So that adds the tokens together. And now we have to do a very interesting thing. We have to try to explode, right? So first we're trying to explode things. We're trying to explode, and then once no action above list applies, snailfish. This is actually, this is a good job for the extra loop. I don't know if you guys heard about it, but there is a very interesting thing called the extra loop. And the extra loop is essentially just a while loop, right, without any particular conditions or anything like that. And it's just basically a bunch of guards, right? So there's a guard 1, and then the body of that guard, and guard 2, guard 3, and so on and so forth. So essentially, it evaluates the guards, and it picks any of the guards that evaluates to true, and then evaluates the body, and then repeats that process. And it repeats it until none of the guards evaluate to false, right? And it sounds like a very simple data structure, but there's so many use cases when it is very, very convenient to express loops like that. Actually, it's insane. And you usually don't notice that, but if you look for it, it's there. And this is basically the case, right? So essentially, you would have two guards, right? So we're going to try that, and then you're going to try another one. So usually, Dijkstra loops are not implemented the way Dijkstra described them. Usually people just check each guard's sequentially and pick the one that evaluated to true and then ignoring the rest of them. As far as I know, the original Dijkstra loop was that the order of the guard evaluation is not important and it's actually not known. And he also developed like a mathematical framework to prove that even though the order is not important, you still can prove that particular algorithm will have determined outcome or something like that. It's he wrote a whole book about that actually. So anyway, it's just like something that reminded me of this thing. Okay, so what we can do in here is essentially we can actually kind of simulate the Dijkstra loop in some sense. So while true, if explode tokens, right? So how do we explode the tokens? Right, I can just do something like that. If explode tokens, explode tokens, so this must be actually DST because it modifies that thing in place, right. If it explodes, this one is rather interesting because the guard is also the action, right? So the guard is also action. So if it does not explode, try to do split tokens. So I'm gonna put it in here. Then this is DST, DST size. And we also need to keep track of DST capacity. And this one has to be something like else, right? If it doesn't explode, try to do split. If it doesn't split, break. So this is something like that. We can emulate that loop like this. That's probably why Dijkstra loops never became popular, because you can just like simulate them, right? You don't really need a whole construction just to have something like this. So yeah. Furthermore, if we had short circuiting, but we don't, we actually don't, I could do something like this, explode or split, and just remove everything. So I could do something like that, but I can't do that, so I have to do it like this. Okay, so after that, I suppose that's it. So there's nothing much to do. Right, so after the first, I probably have to do first false. Maybe I want to actually call it something like init. It's a little too late. Okay, if the first, I assign the DST. If it's not the first, I read the SRC and I add SRC into DST, and then I perform the explosion and splitting, explosion and splitting. After that, I might try to print the tokens. Right, how do you print the tokens? Print tokens. Just to see how they look like. And if this thing is correct to some extent, at least. Okay, okay, so expected expression, but really? Okay. Oh, I see. I'm an idiot. Okay, so I could have just done it like that then. So, all right, and this has to be a DST. So I'm already solving this problem for 3 hours. So obviously I'm like, it's actually more than 3 hours, but I'm already phasing out. So is that I think it is. Holy shit, I think it is. Okay, wait a second. So let me try to do the TMP. I wonder if we can just do something. Okay, so I already copy pasted that. Let's query replace this thing with this thing. Then query replace this thing with this thing. Query replace this thing with just that. Then space close with just close, and the space with comma. And well, okay. So and then if I take a look at this stuff, oh shit, it's not working. Fuck. Wait, it might work, bruv. Yo. Woo. Okay, part 1, here we go. But we need to compute the magnitude of the tokens. Alright, so let's actually write this code. Holy shit. Okay. So let me see, it's gonna be int 64 magnitude. So let me do that one more time. Magnitude. The magnitude of a part of a pair is 3 times the magnitude of its left element plus 2 times the magnitude of its right. The magnitude of a regular number is just the number. Okay, so let me try to do that. So it's gonna be token, and we accept the tokens. Actually, let's call it SRC, right? So and it's gonna be I64 SRC size. Okay. And here is the thing. So we kind of like parsing, we kind of constantly consuming the entire thing, right? Which means that I probably want to do that, right? Because magnitude should be able to tell me where it stopped, right? It should be able to tell me where it stopped. So I64, maybe it's going to be something like token pointer end, right? So, and this is like where it stopped. And by default it could be null, right? So it's just like if you didn't provide, you probably didn't care, so whatever. And let's check the following thing. So first of all, SRC size should be greater than 0, and if it is less or equal than 0, this is basically a mistake. Magnitude of an empty sequence of tokens, right? There we go. And then I suppose I can just return 0 in that case, right? So I just like do something like this. This is my way of doing assertions. It's kind of dumb, but it is what it is. And if SRC is greater or equal than 0, this is a number, right? This is a number, and I can just like return it as a number. Right, so I just, so I probably need to set the end. And if end is provided, I'm gonna do end SRC. Shit. I mean, if everything's okay, I guess we can get rid of this SRC. So we're gonna lose the ability to know when we overflew or something like that, but that's fine, I guess, for now, because I'm gonna spend even more time trying to do this stuff. So SRC essentially +1, right? So this is the end, and then we just return the value of that SRC. If it is, it must be open thing, right? So else if SRC equal token open, right? We're gonna do that. Otherwise, this is straight up unreachable. Unreachable in magnitude. Right. So this is straight up unreachable. Okay. So it's gonna be open, and then I can try to do like a magnitude. Magnitude. SRC, but I also need to keep track of the end. Right, so and P, right. So, but I do care about it though. So it's kind of interesting. All right, so I'm gonna say give me end p. Right, so this is the end p. That's basically A and B. A, magnitude and P. Another one. And if and is available, I'm going to do end P. Is it a good idea actually? Yikes. Might as well actually do something like this. SRC and P. And then SRC and P again. Yeah. Though, doesn't matter. Okay, so, and then I have to return 3 times the magnitude of the left, right? 3a plus 2b. So that's the thing. That's the proof. That's the proof. Almost. Because after that, we should have a closing thing. Right, so that means I have to do something like end p plus 1. Though I can do something like that. Look. If I do something like that, I can literally use the same code like here. Yo, bruv. That's cool. Yeah, something like that. Probably. I don't know. So part 1, magnitude is going to be magnitude of DST, and I don't care. It's gonna end anyway. Right, so the size doesn't matter in that case. Okay, so let me see, and something went wrong, and in here, okay, so it's seg faulted like completely. I see, that's very cool. I really like when this shit seg faults. Okay, so this one is rather unreachable, so that means here I can at least return 0. Did it say unreachable though? It actually never said unreachable, so something is terribly wrong in here. Okay, don't quite understand. So this is because of the magnitude, right? So that's for sure. Yeah, it is because of the magnitude. Might as well try to do the following thing. I can always go to blasphemy.sh and add some f sanitize memory, I think. Yeah. So that's a load of shit. Stack Overflow on... Okay, it's just Stack Overflow. I see. So that's cool. It just simply doesn't know when to stop, right? It simply doesn't know when to stop. Though stopping should be relatively easy, right? Shouldn't it? Because, yeah. So this is a straight up stat, deadly signal. Deadly. Alrighty, so what do we got? Don't quite understand. If the current SRC is greater than 0, the end P is going to be essentially SRC plus 1. So, and we just... Oh, I see. Okay, I'm an idiot. Because I'm already tired, so probably need to make a small break. Still does not work out. Okay, so I'm sort of like remembering that, then... well, I mean, it doesn't matter, isn't it? Yeah, it doesn't matter. So if that is true, so return. Okay, so if SRC is token open, I do that thing, and I get end P. Right, I get end P, and then I assign it here. Then this is the new one, I assign it in here. So, and if end was provided, we return it as SRC plus 1, and we return this thing. Man, what the hell? Really? So, okay, so my brain is phasing out, so... Maybe I'm gonna try to, you know... Let's actually try to debug that. I can always debug that, actually. Right, so AoC 18, GDB main, right, and can I break on main? Actually, I can try to break on magnitude. Oh, I don't have a source. Okay, so let's go to blasphemy and GGDB. Okay, cool. So what did it say? Return a SOC. Break magnitude. Oh, it's a C++. It needs all of these signatures and stuff. Okay, so let me take a look. So this is SRC, and if I take a look at the first one, it's -1. Cool. It goes in here. All right. And yeah. I see. So maybe I should try to do a very simple thing. Right, so let's try literally 2 and 2. Because I'm pretty sure it's something dumb. Like I'm 100% sure. And I just can't see that because I'm tired. Right. So let me see. So SRC, it's an open one. Okay. So then I'm gonna do that one more time. Right. So, and let me take a look at SRC now. It's still -1. Wait, I see. Now I see. Thank you, debugger. Very cool. So essentially it has to be +1. So yeah. Yep. Very easy peasy lemon squeezy. Right, if I try to do that thing now, it is 10, right? So I can't argue with that. So it's a 3 times 6 plus 2 it's 10. Can't argue with that whatsoever. Thank you so much. So this is part 1, by the way. Still on part 1. Holy shit. Why would you give it such a task? Like, holy fuck. It's probably maybe there is some sort of a trick to that task, right? If you know the right data structure, right? If you know the right data structure, it is super easy. Of course, it is super freaking easy. So let's actually run the AoC in HolyC. So let me go here. Run AoC. Okay. Alrighty. So let me see. So drive C. Okay, guys. So this is the 18, and if I try to open this thing and if I try to run it, it's 4140. So the entire thing compiles in TempleOS. Okay, so the indentation with 4 spaces actually looks pretty good, but it's kind of difficult to pull off in TempleOS editor. So, what about the input? 2907, which is kind of sus, right? It is in fact kind of sus. Let me actually print the final result just to see. So this is going to be print tokens, right? So print tokens DST size, and I suppose that should be it. Print a new line, right? So here is the final thing in input, right? So, and it's not the same as the rest of the stuff. Okay, so that was relatively fast. Let me double check the sample. 4140. 4140, and then the input, it's 2907. 2907. First try. Holy shit! Oh! Why would you do that? This is so bad. Oh my god. Anyway, so I cannot imagine what kind of torture are we going to have in a part 2. Hopefully not that much of a torture. Okay. You notice a second question on the back of the homework assignment. What is the largest magnitude you can get from adding only 2 of the snailfish numbers? Know that snailfish addition is not commutative, that is, okay, can produce a different results. Again, considering the last example homework assignment above. All right, so notice that the second, okay. Get from adding only 2 of the snailfish numbers. It's not that hard, I would say. I think it's not that hard. Right. So should be doable. Okay. So I wonder how we can do all that. So maybe I don't even need a break. So maybe I'm gonna do that within the entire thing. So main amount AoC and all right. So let me see AoC. Cool. So we only have memory like for a single one. So I need to think, how can I have an array of them? Because I just need to do like a loop, right? You see, like, oh, like a quadratic loop? Yeah, quadratic loop. So I can basically allocate more things and just like read everything into that, right? I can just read everything into that array. Instead of SRC and DST, we can have something like that. So, all right, so here's the SRC and DST, and okay, let me revert. So of course, we're gonna take a look at the sample though. Token, so tokens, we can have a bunch of tokens. So the token capacity is basically that. And we might have actually like this, right? So we're not gonna have that many of the tokens anyway. Tokens capacity, so yeah, just allocate more RAM. Just allocate more RAM. Okay. So this is part one. What about part two? So I'm gonna actually do something like this. So this is a part two, and in here, that one should be easy actually. You don't need first anymore. You don't need any of that stuff. And then we can have something like I64 tokens CNT equals 0. Though we can actually keep that thing up there, right? So it's gonna be I64 tokens CNT. Part 2, that. And essentially what we're doing in here is just like this, right? So here are all of the things. So token size, it's essentially, oh shit, we also have to keep track of all of the token sizes, I see. So there has to be I64 token SZ, tokens SZS, and that's basically what we have. So this is the amount of these tokens, and for each one we have the size of those tokens. Okay, that's cool. That is very, very cool. So now I can do tokens SZS, tokens CNT, right, tokens CNT, and I chop the tokens out of the line into tokens tokens CNT, and here's the tokens capacity. We keep track of that, and that should be it actually. Right, that should be it. Okay, so then I can print, well, I mean, after that I can do something like tokens CNT++. Okay, so print red d, let's put it like this, tokens CNT equal LD, tokens CNT. Cool, so let's actually see how many we read. Yes, why you keep asking me shit? I don't understand. What do you want from me? So save file, no, what Emacs, shut the fuck up. What are you doing? Just restart. Okay, Emacs is dead. No, just die. I'm gonna kill it, stupid Emacs. Alright, so Emacs, it keeps asking stupid questions that I don't care about. Okay, AoC, alright, something like this. Can I compile this entire stuff? SH, alright. And then if I try to run the entire thing, right, so what is it going to tell me? Tokens 10. So do we really have 10 of them? Let me see. So this is going to be 10 of them. Okay, so there's too much, I would even say. Too many new lines, and this is 10 of them. Okay. Main. It's already closed. It never opened it. Alright. So I64IJ. Right, so this is what we have in here. And let me try the following thing. I'm gonna do I0 less than tokens CNT. So this is the first one, plus I. Here's the second one. So this is going to be J. J. If I not equal J, we're going to do that. Cool. So, and essentially I want to do mem copy, maybe mem cpy. So the destination is going to be the DST. The source is going to be tokens I. Right, so this is the tokens I. We might as well actually do something like this. DST size is the tokens size Si. So this is what we got. And I will probably need to allocate DST size. DST SZ. We also need SRC SZ, I think, at some point. That will be interesting. So the source is this, and how much we want to actually do that as DST size multiplied by size of token. Right, so that's what we have. So we copied that thing in there. And now we just need to repeat this entire thing, right? So we just add and keep exploding shit. All right, keep adding and exploding shit. Okay, let me try. So add token DST size. It might be modified token size, and in here we have tokens. Actually, J. J. Token size J. Cool. So we need to copy that into the DST because it's going to be kept modified. It's going to be kept modified. All right, so then we add them together, and there we go. So after that, it makes sense to compute the magnitude, right? So we're computing the magnitude. And that magnitude is going to be basically, you know, added to the final result, the largest magnitude. Okay, so let's have something like I64 result, which is I64 minimum, right? So this is going to be something like that, right? And then I can do something like result, min I64 result this. Cool. And then this is going to be part 2, right? So it's just like using machinery that we developed in the previous part to solve the second part. So we're just reusing the same machinery, I would even say. So we don't have I64 min, which we'll probably need to add to the blasphemy compatibility layer. So let me see. I can define something like this, and if I remember correctly, it's essentially C min int 64 or something like that. Pure C. Please. I don't remember. I wonder if we can do int 64. Okay, int 64 min. Okay, looks like it is the thing. It looks like, okay, int 64 min. Can I do something like that? Okay, so we need to have mem copy. That's cool. Let's define mem copy. I don't remember what's going to return. I suppose it's going to return this thing. Does mem copy usually return? It does. Okay. U8. I think we'll have to do void on this one. PTR1. We can use void here because it's compatibility layer anyway. So return, and we'll have to cast this entire stuff. U8 memcpy pointer 1 pointer 2 size min I64. Okay, so let's also implement that for the compatibility layer. I64 I64A I64B. Return A less than B, that means we return A, otherwise B. Right, so we return the minimum, and wait, we return the maximum. Largest, okay, so we need maximum. So it means we need to swap this thing around, and this one is going to be the maximum. Right, and then in main.hs, this has to be the maximum. Okay, so this question mark. This one, SOC was never needed. Oh, right, so this is the sample. 3993, okay, that's cool. This one is interesting actually, can I time it? Okay, so it's actually 13 seconds, 13 seconds. That's relatively fast. That is relatively fast. Okay, so let me actually try to look for the actual result, but in TempleOS, right? Okay, so I'm gonna start the TempleOS. And yeah. I pressed something in the middle of booting up, so it could cause. Okay, so I pressed something in the middle of like booting up, and it just like caused the crash, I suppose. Thank you, TempleOS. There's also this shit. Oh my god. Okay, main.hc. So if I try to, it's already using that. Yeah, it's already using sample, so we can just run that. 3993, that's cool. So now, if I try to do the 0, right, it's 4690, 4690, 4690, and if I submit that, second golden star. So yeah. I guess the trap of this problem is essentially the author wanted you to trap into doing binary trees, right? As soon as you start doing binary trees, you're screwed, straight up, because like there's no way you can do that in binary trees. But if you interpret this literally as a sequence of tokens, it becomes really easy, right? So it becomes really easy because that's basically the definition of the rules that you have to follow. Okay, cool. And especially with the compatibility layer now with HolyC, it was a little bit easier now. So I think I'm going to be using that compatibility layer from now on. Oh boy. All right, that's it for today. Thanks everyone, and I see you on the next TempleOS challenge. Love you all.